Y ahí le puse.
¿No tiene que conectarse Pim o María? ¿Antes?
Sí. Pero quedan 2 minutos en teoría. Para...
Bueno.
Sí, sí funciona. Medición, eso no es lo que me preocupa.
¿Y Martín? ¿Alguien le habló? Ha llegado el Carlos Castillo.
¿Le hablas tú o prefieres que yo?
Y ahora yo.
Oye, cuando llegue la autoridad empezamos a hablar en inglés.
Me parece. Oh, shit, ¿por qué estoy sin mi fondito lindo? A ver. Voy y vuelvo. ¿Aló? Sí.
Hola, hola a todos.
Ya.
Hola, hola.
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 So we're close to the opening for Excel. And to start also, I want to know if you're well. How are you doing? We have all the people here. Consuelo, Rocío, Carlos, Martín. Everyone's here. So cool. Thanks, Pim, for your attendance to the event. It's very
No problem, my
meaningful for
pleasure.
us. Thanks.
Okay, so let's start, no?
Yeah, I think so.
Okay. So welcome everyone to the first IBM Networking, an event devised in 2019 by the first generation of postgraduate students of the IBM. Our IBMers community was founded with the interdisciplinary and collaborative work in mind, and we initially wanted this event to be a face-to-face event with networking, presenters, discussion groups, and workshops. But due to the pandemic, we're doing it online. This event is aimed to spread the word of the research of the students across the national and international IBM community. We want to repeat this event annually, making it an important event in IBM research and gather more universities and researchers with more international speakers. We hope you enjoy and learn and benefit of this event. Next, I want to present and ask Pablo Irarrázaval, our IBM director, to give us some words.
Thank you, Axel. And thank you everybody for organizing this and for inviting me to say these initial words. First of all, well, I know many of you, but still I think it's good to give you a welcome to the Institute. The Institute, I mean, the PhD program is hosted in the Institute for Biological and Medical Engineering. And as you probably know, this institute is very special. It has particularities. First, it's new. We are in the process of growing. Probably, I mean, if we compare the institute to the human development, maybe we have 11, 12 years. We are kind of like in the puberty, I suppose. So we are experimenting some problems of growing. We are experimenting problem of space, for example. We are getting a little bit tight. We want to do big things, but we're not that big yet. So this is a very exciting moment to be in the Institute, and the graduate program is a great, is one of the most fundamental part of this Institute, because it's where the motivation, energy of all of you is contributing to this research we're doing, together with the faculty with their own research projects. So in this context, organizing a meeting like this is very important, because you get to know each other. And I think you are giving us faculty a lesson, because this is something we should do much more often, different, I mean, with among faculty, among students, but also together. So in the future, I suppose we're going to need to merge these initiatives in a big event. And so that's probably a challenge for next year, hoping to do it face to face. Yeah. So thank you again. And I invite you, some of you are already working in the Institute. You can go. And so just use as much as possible that possibility of going to the labs, and also to change a little bit of environment, huh? Get out of the house and go to some place else. So thank you again for this workshop, and I hope you have the best of the times.
Thank you, Pablo. Next, well, Maria is not connected, I think.
Maybe in the meanwhile, we can have a discussion previously to the Maria attendance, to talk about the Institute or thoughts about the Institute that can be good. Now, for me, that I was in between two PhD programs, and I choose the Institute, I think I make the right decision, because the interdisciplinarity is something that I appreciate a lot. I wasn't aware about the relevance of it until I become part of the Institute, and I start to feel that environment that have a lot of interactions between different people I think is quite uncomfortable at the beginning, because guys of math talks math, guys from biology talks biology, guys from images talks in images and Fourier. So you kind of figure out how to relate to these people, how to talk with them, and that's very nice. I feel that I'm coming home in institute, and I'm glad that I have a lot of people to talk about different problems, to talk about math, to talk about biology, to talk about coding, to talk about everything that you possibly imagine. You can find a person that knows something about that in the institute, and that's very cool by my side at least. I don't know if someone of you have another experiences in the beginning of the institute that want to share in the meantime.
So maybe another thing that happens is that sometimes you have like a same concept, for example, orthogonality, and it has like similar meanings but applied for different fields. And I found that if you have like not just from one field the knowledge, but also how it is applied to biology, to images, to geometry, you have like a more richer knowledge and capability, as you say, Gonzalo, to communicate, to solve, or to create new things. So that's cool.
Yeah, I think Maria already connected. Hello, Maria.
Hello, how are you?
Fine, thank you.
Good.
And you?
Good, thank you.
Well, we have already made our introduction with Pablo Irarrázaval, so I want to also ask you to give us some words for this presentation and for this networking.
Great. Well, thank you for inviting me over. It's really an honor to be here. I know you've put a lot of effort organizing this, and I really appreciate. I think it's a great opportunity for you to connect, to meet with each other, and to really start collaborations and help each other, especially in this situation where it's not so easy to have like random conversations in the corridors of the institute. So really congratulations. I know it's a lot of work and I hope it's really successful and you really get to know each other. And also I would like to invite you not to only like show off your work and show how nice you're doing, but also show your struggles and say, where do you need help? So you can really start collaborations and raise your hand and say, well, you know, maybe I can help you here and there. And you can start some connections. So really congratulations to all of you for putting this together after months of organizing, and best of luck with this symposium that I hope is the first of many others to come.
Thank you, Maria. And well, I will remember you that the schedule of this event is in our GitHub website. We made 3 thematic blocks. First, the quantitative physiology. Second, the medical imaging. And last, synthetic biology and neuro. Each presenter will have around 5 minutes for presenting and then some time for discussion. And for our first presenter, I will introduce Martin Miranda. He's PhD candidate of our IIBM community with focus on quantitative physiology, and his work title is Syncope, Underlying Mechanisms in the Autonomic Nervous System and Cardiovascular System Interaction.
Wait a bit,
Please,
Axel. I think first Maria should be presented for his keynote speaker. After Maria presentation, we should go to Martin.
Sorry?
do you present Martin, right?
Yes.
So first comes Maria keynote.
Oh, sorry.
No problem.
Can you present that? I don't have it in the.
That's the commutative property. So the order of factors doesn't affect the product.
Okay, yeah, so go to Martin if you want. Martin, are you ready?
Yes, no problem.
Okay, let's use it then.
Oops. Okay. So good morning. And thanks for being here. My name is Martin Miranda, and now I will talk about my research, that is syncope, underlying mechanisms in the autonomic nervous system and cardiovascular system interaction. So first, what is syncope? It's a very common medical problem. It's defined as a transient loss of consciousness due to cerebral hypoperfusion, characterized by a rapid onset, short duration, and spontaneous recovery. As you can see here, it has a great prevalence and represent 1 to 3% of emergency department visits. It also has a great impact in quality of life of people and economic impact too, about 2.5 billion of dollars per year. There is no complete understanding of the main mechanisms associated with this disorder, nor a gold standard for accurate diagnosis in emergency department. So it's a great medical problem, health problem, and theories about the main mechanisms associated with it. And I align toward the theory that the decrease in peripheral resistance is the most important mechanisms that trigger the syncope. So to study this, I taken 60 subjects, healthy and with vasovagal history, and between 20 to 30 years of age. And they undergo a series of autonomic tests that is, you can see here, deep breathing, Valsalva maneuver, and graded tilt test, with the aim to analyze sympathetic and parasympathetic branches of the autonomic nervous system. You can see here how in red and yellow how is divided these two branches, sympathetic and parasympathetic. So the idea here is first with Valsalva maneuver, the subject do a forced expiration against a closed pipe until reach 40 millimeters of mercury. And then in the deep breathing, they just do long expiration and inspiration of 5 seconds for 1 minute. And graded tilt test, they start in supine position, horizontal, and the subject is rise up to several degrees to study these two branches of the sympathetic and parasympathetic nervous system. So then I will use non-invasive and minimal invasive devices to study this activity. For example, FinaPress for beat-to-beat blood pressure measurements and microneurography for recording of the peripheral nerve activity, in this case of peroneal nerve in the leg. Also, I will use electrocardiogram and belt for respiratory activity. And the approaches are two. First, a synchronization approach in which I will see this physiological signal as self-sustained oscillators. and I will calculate the instantaneous phase in order to see the interdependencies of the signals using the phase logging approach. So the idea here is study how these electrocardiogram, blood pressure, and respiratory signals are integrated in my brainstem, and how these produce differences in the response of sympathetic nerve activity in the legs. And on the other hand, I will build a mathematical model using ordinary differential equations in a physiological based model to try to understand how these signals are integrated and how these produce a response in muscular sympathetic nerve activity, MSNA. That is this signal here. So with a full understanding of the mechanisms underlying syncope will open possibilities for a new diagnostic method and therapies, and allow us to understand how complex systems such as nervous and cardiovascular system interact with each other, and how this implicates in the study of other autonomic disorders. So you can see here the future work is training on this technique that is impale a nerve, the peroneal superficial nerve, using these very tiny microelectrodes. That is very important for this research. And you can see here one of the subject under tilt test, and the subject faint. Just here, you can see how the map, the mean arterial pressure decrease rapidly to very low levels. So this is what about my research field. So now you can ask any of those questions.
I have a question to kickstart this. So one thing that catch my attention is why people go to emergency when they have syncope.
Okay, maybe one can see the syncope as a very non-important problem, but 10% of the visit of emergency to the emergency department has a very, how to say, a bad end that include the death. It's not a problem that could see as just episode. It needs a lot of tests to be sure that there is no related to other pathologies that could be more serious. So that is why a lot of money for a study is used, and usually the MDs are not totally sure about the diagnosis, so they need a lot of other exams that maybe are not necessary, and this produces the high cost of this pathology. There is not a gold standard for the diagnosis, so it's based just in the history of the subject, and based on if during the faint other people see what happened, so they report more information. But usually they go and be they indicate hospitalization to be sure that there is no other problem associated and it's just an episode. So it is because in general it could be summarized as a lack of certain on how diagnosis this phenomenon.
So the approximation is basically something like save money by developing new methods to detect syncope. It's basically that, right? Like instead of do a lot of exams and don't know what is happening, have a new method or couple some method to detect syncope easily, right? Or more easily.
Exactly. There's a lot of I don't know, new ways of diagnose, prevents therapies that are needed for this pathology, for this disorder. So yes, for example, a good tool maybe is form to um, with a device, for example, try to anticipate to the event, to the faint, in base of these physiological signals. But until now, there is not a good accuracy of these devices, so are not used for the subject. Yes.
Okay, and why the subjects that you have need vasovagal history?
Okay, yes, because I want to compare healthy people and people with this pathology. In fact, it's the subject just have to be a story of one faint episode in the last year. Is to be sure that I will have people that faint and people that don't faint. Is to separate in the two groups, control and with the disease.
And my final question, and like I don't know, comment is we also work with oscillations and analyze oscillations. I think a lot of people here do oscillations and analysis, so it's kind of cool. And also maybe there is an opportunity in open hardware to develop I don't know, some tool or a low-cost diagnostic tool that can help in this problem.
Yes,
so
for example,
I offer my help for future development of open hardware in IBM projects.
it will be great because, for example, for diagnosis, field tests take about minimum 30 minutes until the subject faint. So if you can reduce this time with a form to predict the faint without the faint, it will very important for the subject. And also people that usually faint, a device that indicate you when if it is a great probability that you faint in I don't know, 1 minute. People can take all the I don't know how to say, but todas las medidas to avoid, for example, people sit in the ground or take position to avoid the faint. So if you can predict the faint, it will be very important.
Great. Other questions?
Hi, Andrea here. So I don't know who's moderating this session. Because I don't know how to ask questions. I was raising the hand in the thing, but so please advise how you moderate with these things. Okay, now Martin. In the meantime, what I wanted to ask you is so first of all, nice work and nice presentation also during your qualifying examination. wanted to ask you if you can somehow forecast what will be the major challenge that you're going to face in developing your project.
The major challenge, I think that maybe will be the experiment period, to start the experiment first with context that we have now with the COVID. And second, because all these measure and device need a very high quality, and that the protocol being very I don't know, that each of the device have to be put with very accuracy to get the best signals, to get the best results. So with all these tests, it's a lot of movement of the patients or the test, for example, the TIL test. So maintain the condition for the best signals quality is one of the most challenge, the high challenge maybe that I have.
Cool. And how are you going to, so do you have a de-risking strategy for these type of challenges? What would be your strategy to overcome it?
To cover the challenge, well, I now, for example, I'm working to avoid that all these maybe problem, to see this problem after to do the experiment, and with a lot of practice, I think. Now I have programmed the start of this test in the second semester of the next year. So now I can start to make preliminary data with subject, maybe without the microneurography, because the next semester I go to train in this technique, but to start with the other test and start with this data and start to see what kind of problem maybe it could be necessary to start to work. And this type of test as clinical test need a lot of practice to make the best quality of the results.
Okay, cool. Thank you.
Questions? Yeah. Okay, so let's continue. Now I want to present Maria Rodriguez. I want to invite Maria Rodriguez, our IBM postgraduate director and keynote speaker, presenting mathematical and computational tools for understanding biomedical data.
Thank you, Axel. I'm going to start sharing my screen. Let me know if it works well. So give me a second. Okay, can you see my screen and my cursor?
Yes.
Yes.
Okay, thank you. So thank you for the invitation. As Axel said, I'm Maria Rodriguez. I'm a professor of the Institute and also the director of graduate studies. And today I'm going to show you a little bit of what we do in my group. And our research is really diverse, but we have always a leitmotif that is mathematical modeling. So it's great that actually Martin already presented. He is one of my students, and you could already see this combination of experiments plus computational modeling. So we try to enhance our knowledge with this combination. I want to start showing you this illustration. I find it a great illustration from Olaf Wackenhauer. He is a professor of the University of Rostock that I really admire, and is one of the fathers of systems biology. So here he illustrates the use of systems biology, although lately we've heard about systems medicine, systems pharmacology. So there are like all the systems approaches for many traditionally experimental science. And here he calls for a systems approach and says that is the realization that we must go beyond the characterization of the parts and knowing interaction partners. So basically, the idea of using this systems approach is that function is not a property of parts, is a process of spatial and temporal interactions. So for understanding these interactions, it's not enough to just collect data and maybe we can turn this data into information with proper data analysis and bioinformatic tools, but also we need to build models that are going to allow us to perform different simulations. And with these simulations, we can test different hypotheses to really better understand the dynamics of the system. So the idea is that models can guide data collection and allow us to distinguish between alternative hypotheses that can explain the current observations. So this is kind of what really drives all our research in many different aspects. And also introducing like why model, right? This is a question that many people wonders. Why do we even care about modeling if we have data? Well, there are many reasons for modeling other than predict. And some of my favorite answers to this question comes from the paper from Joshua Epstein that I definitely encourage you to read. And he says that every time we make a prediction, for example, a clinician that is predicting how a patient is going to evolve, or every day us or in the news, how this epidemic is going to unfold, we're running some models. So sometimes, most of the time, this model is implicit. We don't really explicitize all the characteristics of the patient and the disease that make the clinician decide on one treatment or diagnostic or another, but there is always a model behind. So one of the most important contributions of modeling, the modeling enterprise, is that it enforces the scientific habit of rendering hypotheses and assumptions precisely. So we definitely have to write down our hypotheses and build the model based on this hypothesis. And then we run it and the simulations might contradict or not our data. So we might say, well, our data or our model doesn't really go with the hypothesis, or our data don't really go with the model we are suggesting. I'm showing you here an example of one of our recent works where we build machine learning models to predict venous thromboembolism in ovarian cancer patients. So here, the main objective of this work was not really prediction, was not really knowing who is going to have thromboembolism during the course of the disease. The most important part of the work was to understand what are the modifiable factors that influence thromboembolism so we can treat them or prevent them before the event happens, right? I mean, it's important to predict, but what if we can't change the course of the disease? So the main idea is don't really look at the non-modifiable factors, try to find factors that we can change so we can really avoid this to happen. Also, by really needing to handle real data, and this is a work with collaborators, with data from patients in Chile. And we have to take into account that Chile is a relatively small country, so it has a relatively small population. And we need to develop new techniques that allow us to handle this small big data. So we can't really use the approaches that astronomers use with thousands or millions of data points. We usually, when we are lucky, we are in the hundreds of patients. So we definitely, even if we collect data like from every single ovarian cancer patient from Arica to Punta Arenas, we can't really reach the amount of data, of course not the astronomers get, but not even the data that a study in China, for example, can do in a really standard hospital. So we need to use our local data, because we also know that genotypes are different, that lifestyles are different. So we can't really make conclusions about our population based on data from elsewhere. And we want to also make personalized predictions. So one of the main ideas of this work is that if we want to make personalized predictions, we know predictions are not perfect. I mean, if we could have a prediction with 0 mistakes, there's no doubt we'll go for that, but we never can do that. So if we can't do a prediction with 0 mistakes, what would you prefer? A false negative or a false positive? What do you prefer? Would you rather tell a patient that it's going to have a thrombotic event and then the event ends by not happening? Or would you rather tell this patient that it's going to be okay and the thrombotic event happens? And well, there is no correct answer for this question, because really it depends on the situation of the patient. It depends whether the patient is in a remote place without access to a clinical setting, or whether the patient is hospitalized and everything is follow up. So I'm going to give this patient anticoagulants, and if she has bleeding, it's fine. I'm in a hospital and I can easily react and cut it out. But if this person is in an ambulatory setting and is far from the hospital, then maybe I don't want to risk it, and I would rather not give the anticoagulants, and I would rather risk the thrombotic event. So in order to be able to decide like what model is better for each situation, we decided not to give like this is our best model, work for it, but give a set of models so the clinician can choose, depending on the situation, well, I would rather risk the false positive, or I would rather risk the false negative. So that's why we used multi-objective optimization. So we build this set of models that all of them are optimal in some sense. So this is one of the uses of this multi-objective optimization for personalized prediction. Another amazing aspect of modeling is that modeling can help us understand something very complex by simplifying it. So understanding arises from transforming one reality into another, and this is modeling. So we can understand complex systems by abstraction. And the need to make these assumptions and the need to choose the level of abstraction is the art. That's really like the difficult question on where what assumptions are appropriate. Am I simplifying too much? I am getting the proper level of simplification or not. So Picasso used to say, art is a lie that makes us, art is a lie that makes us realize truth. We say modeling is a lie that makes us realize reality. And is this art of making appropriate assumptions. And here I'm quoting Olaf Wochenhauer again, that has an actually pretty active Twitter account with very nice quotes about modeling. So I'm showing you one of these, one of our studies where we went very Picashian, and we needed a huge level of abstraction because we wanted to understand circadian rhythms of blood pressure in humans. So circadian rhythms are pretty amazing. For those unfamiliar with them, circadian rhythms are physical, mental, and behavioral changes that follow a daily cycle. Pretty much every cell in our organism has an internal clock, although the master clock is located in the suprachiasmatic nucleus. And blood pressure is not exempt of these changes. And in healthy individuals, we know that blood pressure follows what is called a deeper pattern. So it increases in the morning, and then we can see it here, it increases in the morning, and then it falls during the nighttime rest. And this fall should be at least 10% for being considered a deeper. And for those individuals that don't have this deep, they are considered non-deeper. And we know that a non-deeper profile has, even if the person is normotensive, is not hypertensive at the time of detecting the non-deeping pattern, this person is very likely to have cardiovascular events in the following 5 years. So we say, and astonishingly, cardiologists, if they find this pattern, they know it, but they don't really treat it. There is not really like a protocol for treating non-deeper patients because they are not hypertensive. So they just wait until they develop hypertension, what I think is kind of too late. Why not to treat it before, and why not to investigate the causes of this non-deeping profile that are also very, very different. So what we did in this study is to create this mechanistic model that is based on also ordinary differential equations, as the model that Martin was presenting before. And we wanted to include some variables that definitely influence blood pressure, but we needed to keep this balance, not to make the model too big or too complex, because we couldn't have enough data of every single system that is involved here. And if we don't have data, the model is going to be unidentifiable, the parameters, we will have problems estimating the parameters. So we needed to kind of balance the level of abstraction, so we could include physical activity, vascular resistance, blood pressure, heart rate. And interestingly, this also lead us to one of the other reasons why to model, and is guiding data collection. So from this exercise, where we started using data from literature, we designed the setup of our next experiment, where we decided to include some of the variables that our model and our sensitivity analysis also informed as very relevant for this, for explaining blood pressure, or the circadian rhythm of blood pressure. And one of the results from this data collection protocol was this work, where we tried to identify larks and owls among the IIBMers. So we actually, I know we had a lot of you participating in this study, and we used a lot of ambulatory sensors. You can see here this sunsprite that was sensing light. We were also equipping the volunteers with an equivital that sensors electrocardiogram, breathing rate, skin temperature, among other variables. We were also giving them an ingestible core temperature pill, so we could follow the internal temperature over 24 hours or more. And we were also, of course, measuring blood pressure over 24 hours. We were collecting saliva in these salivates that then we were analyzing at the lab. And with that, we were able, I mean, the idea of this work was to see whether we could predict the circadian phase of our volunteers, whether they had a preference for working in the morning or working in the evening. This is like what the chronotype means, and the extremes are called owls and larks, but of course there is a wide range in between. So we can extend a certificate saying, I'm always late at AM class because, you know, my genes, I'm an owl. So we can do that in the next experiment if you want. But well, the idea is to be able to predict the circadian phase with the less invasive pieces of equipment. So we took a lot of data, but then in our models, we simplified that so we could really keep the minimum equipment. And for example, the saliva samples that were used for calibration were no longer needed for predicting. So we could now perform prediction only based on activity patterns and heart rate variability of our volunteers. And this can serve, you know, like for companies that work in shifts to really decide who are the people that should be working in the morning shift, because they are going to have a much better performance, and who are more suitable for the night shift because really they have a preference for that shift, and that can decrease accidents, etc. And I could share with you other examples, but I'm just finishing with not so biomedical, model-driven data collection. So here we used also an iterative approach for optimizing physical-chemical properties of a multiple nanoemulsion. So the idea is to use always mathematical modeling, optimization that leads to optimal experimental design. So our data collection was guided by these models, and we could achieve very good properties of this nanoemulsion with much less experimental work than in a regular setting of trial and error. So now it's time for you, students, to present your work. I just hope that I convinced some of you that models are a way of thinking, and that the purpose of models is not really fitting the data, but to sharpen the questions. So this is really what we look for in our group. And I can't finish without thanking my research group, amazing students from this community, without whom none of this research could have been possible. So thank you all, keep up the great work. And I can't finish without taking the opportunity to say that applications to our master and PhD programs are open until November 20th. So please spread the word and to anyone that might be interested in embarking on this adventure. Thank you for your attention, and if you have any questions, I could be more than happy to answer them.
I will start here with a question about which other biological rhythms are interesting for you or your research.
So we are now studying particularly blood pressure. By the study of the circadian phase itself, we actually study everything, because it's like the big manifestation of circadian rhythms, and is this preference. So also something that we want to study now, and we are starting to collect data, is glucose patterns. So we are going to start a new project that aims to develop an artificial pancreas. that is not only based on previous measures of glucose, as current artificial pancreas do, but also take into account activity and other physiological variables, and also circadian rhythms of all these signals. So basically, I haven't seen in all this pancreas research, usually people tend to keep the glucose among a certain threshold, but I haven't seen them trying to replicate what really happens in healthy subjects. And I have the suspect that by just putting it very flat, you are not really helping the organism, because these rhythms are very necessary. So you need to have low glucose and high glucose, of course, within certain ranges. So we're trying to replicate this with a new model that hopefully can sometime and someday be put in an artificial pancreas device and decide on the insulin that is provided to each people with diabetes to really improve their health and lifespan.
Thanks, Maria.
I think Carlos Castillo has a question.
Yes. It's a very simple question. When you say that you use activity in your models, how do you measure activity like in real life? When you put someone in a bike, like doing something like this, how do you say this is like 3 activity or 2 activity?
Very good question, actually. So we this equivital, I didn't mention with the sensors of the equivital, has a 3-axial accelerometer. So then with the accelerometer is measuring, and actually they have a formula that says activity counts, but of course this is a pretty subjective measure, but it's based on the acceleration of the accelerometers that are embedded in the monitor. And it's very relevant also because this equivital gives like different already processed data. And for example, when a person is sleeping, it can give you like zero activity counts. But even when you're sleeping, there is activity. So if you go further and really analyze like the raw data, then we extract this data to be able to even differentiate between the people that are having a very deep sleep and a not so deep sleep, because the activity while sleeping is different. So you can go very, very like fine in that analysis. But it's just processing of this accelerometer data.
Thank you.
Thank you, Maria. Thank you, Carlos, for questions. I don't know if anyone has more questions.
Maria, maybe just a very brief one. If you can comment on what is your modus operandi when you have to choose a model for a certain type of data sets?
Yeah, so we usually we do twofold. One, when mechanistic knowledge is available, that is pretty much always, we try to base our models on literature, like papers, publications, knowing everything about the system we want to model. So we incorporate this information into our model. And another very important piece of information is the data that is available or is accessible. So even if it's not available, whether we could ever measure it or not, because we could incorporate like thousands of variables that we are not really able to measure. And it is okay to incorporate a couple of variables that we are not able to measure because we can infer one from the other. But if you incorporate 100 of variables that you can't measure, then you can't really distinguish who is driving what. So we need to keep that balance between data that is then used to calibrate the model, because without data, the model doesn't really hold, and information like in the source of papers and literature.
Perfect, thank you.
I think there was a question, Gabriela, or not?
Yeah, one was a similar question about how you build the models. For example, in the data that you present, you work with 10 models. So it was something similar as Andrea was asking. How about the model and the mechanisms and the parameters has a meaning representation of the physiological mechanisms? And the other is in the experiment that you're planning with the glucose and the artificial pancreas. If you are planning to consider not only the physical activity, but the exercise, because we know that, as you say, in the rhythm and the physiological change that you experience in exercise is quite different, and the impact will change our whole system.
Yeah, absolutely. That's a very good point. So regarding the first question, I could say that, and also complementing the answer to Andrea, all this modeling process is always iterative. So we start with a model and then we feed the model to our data. And if the model is not able to feed the data, then we start thinking whether the parameters are not correct, or whether the model structure, so the hypotheses that are behind the model, are not correct. And those are negative results that are very, very relevant, because it's a way of rejecting a hypothesis, saying, well, really, our data do not fit this hypothesis, so maybe we have to incorporate something else, or sometimes is also a matter of the parameter estimation problem, so more an optimization problem that you are leading to a local optimal instead of global. So you have to balance that. And also there is always a step in this model building that is sensitivity analysis and identifiability analysis. So with the identifiability analysis, we start seeing which parameters are redundant, which are highly correlated, so we can't really distinguish uniquely. And with the sensitivity analysis, we identify the parameters that are really driving the phenomena. So we put more focus on that, and we say, well, this branch of the model is really relevant because the sensitivity analysis said that it was driving most of the results. So we maybe can here put a little bit more attention and give a little bit more detail. But here, that definitely is not very relevant. We can forget about it, right? So, and this is done in the mechanistic models, and also in the more like black box machine learning approaches. For example, in the circadian phase prediction model, we found that blood pressure was not so relevant to our results. So we decided to discard it and not use it any longer, because with activity and heart rate variability, it was enough. And we could also save the patient or the subject from one extra sensor. So it is really iterative, and that's why modeling is also an art. There is not really a recipe for modeling, but that's also what makes it very beautiful. And sorry, your second question, yes, regarding this the artificial pancreas study, we are going to start collecting data now, and it is challenging due to the pandemic. So we are trying to organize an ambulatory strategy. So we ship the sensors to the people at home without contact. We instruct them through Zoom or any other platform to use all the sensors. And then a week after, we collect all the sensors and the data from the volunteers. So we definitely are going to collect as much data as we can, blood pressure, temperature, activity, but it's a very good different. A very good point that you make is different activity from physical activity, from exercise. So we should definitely also incorporate questionnaires that we might miss in a week of data collection, more about the habits of the person, because also like the synthesis of glucose will change a lot depending on the level of exercise of this person previous this week of data collection. So that's also a very interesting point, and also leads to the need for personalized models and personalized medicine that we always take into account. Every person is different, so why to model them all equal? Thank you, Gabriela.
I think, Gonzalo, you have another question?
Yes, I just wanted to know the opinion of Maria about these black box models from machine learning versus stated mathematical models like OD or stochastic models that you know what's happening in the model versus something that does a hidden processing of the data and tell you something. So I wanted to know your opinions on research, and if you have, maybe you use stated mathematical models for some things and maybe machine learning algorithms for others, that kind of things.
Yeah, exactly. I actually use both. I started, or I come from the more mechanistic modeling tradition, but really, like, one cannot be completely blind to the development of new techniques and to also the development of data. So there are so many data now available that sometimes a machine learning black box technique can also tell you a lot. And even if they are like black box, as you say, and you can't see the interaction, you can still identify very relevant factors. And then maybe you can go and model them in a more mechanistic approach. So I think they are both complementary, and I use them depending really on the application and whether I want to just identify factors or understand how do they interact. So I think really they are great tools, both of them, and I couldn't choose one over the other. I think they serve different purposes.
Thanks, Maria.
I think Carlos Castillo has another question, or no? You have your hand raised. No? Okay, so thank you very much, Maria, for
Thank you. Thank you very much for the
your
invitation.
presentation.
It was a real pleasure.
Well, next I have to introduce myself for the next presentation. Well, my name is Axel Sepulveda, and I'm Master of Science student of the IIBM. I'm also a student of Maria, and focused also on quantitative physiology. And I want to share my screen to present you. Should be seeing this. I think you see, yeah, you should see my screen.
Yes.
Well, this presentation summarizes some of my work in the Master of Science program, and it's related to machine learning application to motion recognition using mathematical tools like wavelet scattering. We will see later what is that about. And for feature extraction from physiological signals like electrocardiogram. The title of this presentation is ECG emotion recognition using wavelet scattering. Well, in first place, affective computing aims for the integration of an automatic recognition of human emotional states in human-to-computer interfaces with many applications, from security to the entertainment industry. Emotional states are subjective experiences that are commonly classified in literature in 2 dimensions, typically named as valence and arousal. Valence refers to the pleasant or unpleasant level of an emotion, and arousal refers to the activation or deactivation level of an emotion. One can map any emotion like anger, happiness, fatigue, calmness, using those 2 dimensions as can be observed on the image above. And for example, this arousal and balance determines a 4-quadrant map that has like positive or negative balance and like high or low arousal. And each emotion can be classified or mapped in this in any of those 4 quadrants. Also, one will commonly associate and think of emotion recognition from a photo, a face video, a voice, or even commonly an electroencephalogram. There are many works that employ those as input signals with great success, but acquiring those signals in a real-world application sometimes is not very practical, needing, for example, cameras always in front of the subject to get the face video. You need the subject to speak constantly to record their voice, or wearing, for example, an uncomfortable EEG cap or helmet. That are the reasons why we should search for any other like physiological signal that can be input to a classifier, and that's why what we have done is employing the electrocardiogram signal to raise the hypothesis and see if we can recognize emotions from the patterns of the ECG. And for that, we employ wavelet and mathematical method that is called wavelet scattering. And let's see if that improves the performance of accuracy of a typical classifier. To test this, we employ a published dataset named Amigos, that is acronym for a dataset for affect, personality, and mood research on individuals and groups. It consists of 36 volunteers whose ECG, EEG, and galvanic skin response signals were recorded while watching videos selected especially for emotion elicitation during individual and group sessions. Also, face videos of each volunteer were recorded and later manually annotated every 20 seconds in the arousal and balance dimension by 3 experts. You can see the lab setup of the construction of the dataset. In the image above, there are 2 experiments like individual and group sessions. Well, all the data is then processed in MATLAB, low-pass filtered, and segmented every 20 seconds according to the expert's annotation. Datasets and labels are then balanced because there are more. Usually, you will yield the annotation will yield more labels for one class than another, and that's not very useful sometimes because if you have a low amount of data, your classifier will be unbalanced with respect to the dataset. For example, if you have a dataset with 90% of one class and you classify with a random classifier, you will get around a 90% of accuracy. So you need to you usually need to balance the dataset. Then I applied 2 methods for figure extraction. The typical is time and frequency domain. This is like RMS or interbeat interval, statistics about heart rate and heart rate variability, ratio of the proportion of RR interval of the ECG that is more than 50 milliseconds or it's more than 20 milliseconds. Also in the frequency domain features, we extract low frequency, mid frequency, and high frequency power spectrum. and also the ratio between low and high frequency that is usually reported to be an indicator of emotional state. And this is compared with the wavelet scattering feature extraction algorithm, and that consists or is applied with some parameters. In this case, it consists of 2 filters with 8 wavelets per octave in the first filter and 1 wavelet per octave in the second filter, with an invariance scale of 20 seconds. I think. Oh, I was checking the chat. Yeah, well, and this and that is employed to extract features from the ECG signal. Then all of those features are fed into some classifiers and compared between the distinct classifiers and between the different features of time frequency and wavelet features. All is validated using tenfold cross-validation. Let's talk a little bit more about wavelet and what is this about wavelet filters and wavelet scattering. First, I want you to remember this image about the filter banks that are used. Those functions are used to convolute the original signal and extract the features of the ECG. Well, what is a wavelet? A wavelet is a short duration signal, and that is called to have a compact support. You can have many wavelets, and you even can define your own wavelet, like a custom function. They have some properties. Well, the most important are that they have a compact support and have a 0 average area under the curve. Then we have the wavelet transform, and for this we can recall the Fourier transform that I know many of you are familiarized with that. But what we have to notice about the Fourier transform is that it usually loses location information. What is compensated with the wavelet transforms, because it preserves the location information of the frequencies across all the duration of the signal. Also, as you can apply any function, because, well, recall the Fourier transform equation. You have the exponential that is called the analyzing function of the Fourier transform. In the wavelet case, you have any function that you can determine or create yourself, or you can use a commonly used wavelet that many have some custom names, like the person that first stated them, or for example, their students also have their custom names for the wavelet they created. For example, you have the mallet wavelets, the double cheese wavelets, and they have different orders and different shapes. What is important about the wavelet transform is that it preserves or have some properties, that is translation invariance and time warping stability. This is a desired property used a lot in machine learning, also a lot in image processing, because you want, if for example, in translation invariance, you want an object to be recognized independent of where in the, for example, if we are processing an image, we want the object to have the same features independent of where in the photo is this object. For example, if we have on a square on the upper left, we need it to have the same features like if it is located in any other place of the image. The same happens in signal processing, where we have just one dimension and not two dimensions like an image. And for example, also if we make a zoom or we have a square that is bigger or smaller, also we have it to be the same features as a square. And that is the time or scale stability. And with the wavelet transform, we achieve that. Translation invariance and time working stability. Then we have the wavelet scattering, in which we subdivide the original signal and apply recursively this wavelet transform. So we yield with an extended feature vector, and we can analyze every portion of the signal at different scales of time and frequency. Because something that you may recall from physics or chemistry, that is called the Heisenberg principle, that you can determine a position and the frequency or all the properties of a system if that you can you can get all the properties of the parameters of a system with just one measurement. So you may need to make many measurements or independent measurements of each parameter to get an idea of what you are trying to measure. So what you achieve with this scattering is subdividing the signal and get coefficients or features at different scales. Well, then the features of the wavelet and the time frequency are fed into different classifiers. Well, in this case with the Amigos dataset, we yield with in total 24 features in time and frequency, and with 210 features in the wavelet scattering algorithm. Then we fed those independently those features to the different classifiers. Those are decision trees, discriminant analysis, naive Bayes, key nearest neighbors, support vector machines, and assembled classifiers. And in the first table, I resume the accuracies of each classifier. First, we see that for time and frequency features, the best classifiers are SVM and decision trees. Then we see that with wavelet features, all the accuracies are improved for all the classifiers. Moreover, the ones that get the best accuracy are KNN and ensemble classifiers. This table resumes the classifying in 2 dimensions. This is in arousal and balance independently. And then we can use those classifiers that have the better performance and classify it in 2 dimensions simultaneously. This is in 4 classes. So now we have the full 4-quadrant map that showed you first. And using the best classifier, and in this case is the ensemble classifier, we get around 95% of accuracy using something that is called majority vote. But because with the wavelet scattering algorithm, we create some sub-windows of each original signal. So how we can classify the original signal, we employ those windows as votes. So each window has a classification, and we can use the votes of each window to classify the original signal. This will yield a more accuracy, but with the drawback that we can get a tie in the votation. That is why appears this no unique class in which the algorithm can determine what is the final class of the original segment of the signal. But the overall performance is improved. Next. Well, as a conclusion, the wavelet scattering improves the classifier accuracy for signal analysis and classification of ECG for emotion recognition, compared to typical feature extraction in time and frequency domains. What you should get to home is that maybe you can use also this wavelet scattering approach to improve your classifying accuracy in signal analysis, and may be useful in cases with low amount of samples or hard to identify features scenarios. In this case, for example, I applied the algorithm with around 1,000 samples. In some cases maybe a too low amount of samples, for example, to apply it in a neural network classifier, and also manually extracting those features would be a lot harder and not necessarily will yield the same performance. That is why this wavelet scattering is an improvement in the performance of the classifiers. And what could be done next is, for example, embedding this algorithm in a microcontroller and have, for example, a wearable device that may transmit or recognize your emotional state. Well, that's my presentation. Thank you. I don't know if you have any question.
I could moderate now, since you you will be answering questions. So
Okay.
thank you, Axel, for your presentation. It's an amazing presentation. I don't know if anyone of you have any questions to ask for Axel. If it's not,
I have one.
okay.
So
I have one.
Okay, so Gonzalo next, Martin.
Okay, thanks, Gabriela. So my question is kind of a comment. So what made you choose wavelets instead of another technique? Like, which other techniques do you compare to this in order to use wavelets as the final method to analyze your data?
Well, first, my approach was following other research that employed those time and frequency features. And for example, the original dataset employed heart rate variability, frequency domain, and power spectrum features, and they get a very low accuracy, around 50-60%. And then some other works improve improve this performance with, for example, other classifiers, some others manually extracted features. Finally, some started to employ deep learning and neural network. The thing is that when you employ neural networks, you don't know, or you have like this black box of features that you don't control and don't know what is happening. So that's why first I choose the wavelet. Also, this wavelet is a well, I didn't mention, but the wavelet transform is kind of a convolution. So it's very similar to what is a convolutional neural network, but with with all the weights in the hidden black box is controlled by you. So those coefficients, you don't need the algorithm to learn those coefficients. So first, you don't have to train, and you don't need a lot of data to train the method, because you already have the like the function that extracts the features. So it is easier to classify. Also, this similar method is employed to classify other types of well, also ECG, but not apply in emotion, but for example in arrhythmia classification.
Thanks, Axel.
Okay, thanks, Axel. Now, Martin, go on.
Okay, hi, Axel. Nice presentation. My first question is, why did you choose that feature for electrocardiogram? You choose 5 or 6, I don't remember, but there is a lot of features that you can take from the electrocardiogram in time domain or frequency domain. Why did you choose that special?
Well, in total, I used around 24 time frequency domain features. I found none of them achieved a very good performance, or like better than what was reported on other workers. Because of that, I started searching another algorithm that could improve the performance. I don't know if, well, I know there are maybe there are more time and frequency features, but I think I use the most commonly used.
Okay, it is very interesting because autonomic system is very related to how the motions cause a change in cardiovascular variable. So maybe that is a point that we have in common. So it's very nice. And the second question is how wavelet manage with non-stationary signals, noisy signals, or nonlinear signals. Because I have maybe the same problem to choose the correct approach for my signals. What do you think about this?
I think you should try first. Well, if you have like a problem with like this kind of signals that are hard to extract features, and well, if you apply neural network, you don't know anything about the features that are extracted underneath. So maybe you could try, give it a try to about this algorithm, and maybe you could get some useful features that could be used in your work.
Okay. Thank you, Axel.
Okay, so I have some questions. I don't know if any one of you have another, but one question is related with interpretation of your results. How you interpret the difference of accuracy between using Fourier and wavelets. You have a table. If we can set something from that accuracy terms, like the interpretation of the classifiers, why we have some better results with wavelets than Fourier. And if it's a silly question, the next one will be if you, as you explained to Gonzalo, that could be like a similar convolutional neural network. You could use like layers of wavelet functions. if it is possible to do that.
Well, regarding the first question, there are differences between the Fourier features and the wavelet features. The most important is that when you use Fourier, recall that you apply the Fourier transform to a signal in time, and you get a signal with in the whole frequency domain. You lose all the spatial or temporal information about the signal. So instead of just getting a frequency or a power spectrum with the Fourier transform, you get like it's like similar to what will be a windowed Fourier transform. So it's like taking the Fourier transform every some seconds and getting the power spectrum of every window. But in this case, you make it more continuously. Also, when you make the windows, you produce some discontinuities in the signal with the Fourier transform. So applying the wavelet transform, you avoid all these inconvenients. So you will get like you will get more features, and also you get a detailed set of features across all the time of the signal. It's like Fourier, you get like a photography of the signal, and with wavelet you get a video of the signal, a video of features of the signal. And regarding the second questions, this is something like a chain neural network, because the different filters or the different iterations of in this wavelet scattering is like all the labels of a convolutional network or a neural network. The only thing is that all the parameters are not learned, but are determined by you.
I have another question. If you have like some results of how the classifier classify the emotional states in the whole experiment of the subject. I don't know. For example, you have one subject and the subject could fluctuate through different emotions. Have you like plot, or we can see how, according to your classifier, is the person like behavior?
Okay, yeah.
Like the visualization of your analysis.
Okay, yeah. All the classification is done with all the data. So all the data or all the windows are randomly mixed between subject A and subject B. But yeah, I could do that analysis, classifying or seeing like the emotional change of just one subject. Yeah, that could be presented further.
Yeah, exactly, because at the end we want to know what is the emotion that the subject, like how we are going to visualize and understand that in one subject.
Yeah.
Yeah, great. So I don't know if any one of you has some other questions. If it's not, I think that we maybe should close a little bit earlier this block.
And indeed, we're closing a bit late because this
later?
block should be closed at 11. Yeah. So good.
That's true.
We have a lot of questions. So keep doing that. That's very good for our understanding of other researchers. And so far, has been really interesting for everyone. So I think now we should take a break until 11:30, and then we continue with the second block of presentations. Okay.
So see us in
Go for
a
some
couple of
coffee.
minutes.
See ya.
Okay.
I see you.
Yeah. Thank you.
Hola. Hola, Vicente. Ahora, okay, we will come back at 9:30 of the break for your presentation. I think there are some people already here.
I am. We are ready. Hi,
Hi,
hi.
Vicente.
Hello, so we're meeting in English?
Yes.
Great.
Yes.
Who else is connecting now?
This session is guided by Carlos Castillo, and we will start at 11:30, so there's still a bit of time to people to connect.
Great, thanks for the invitation. And who's organizing?
We all, yeah, it's kind of been a challenge to organize this, but we think that it's relevant to us to know each other research in order to collaborate and to give ideas to other people, to communicate also difficulties in your research and how to tackle them, and maybe you can have more views coming from your partners in different areas. Hi, Francisco. Welcome.
Hello.
Glad to see you here. So we are
Yes.
waiting a few more minutes until the people connect, and we start.
No problem.
Yeah, in the meantime, I wanted to say thanks for the invitation, and I'm sorry I couldn't connect in the morning. Also, I think I'll stay for this whole block, but then I have to have other meetings also to teach. But maybe I'll see the other presentations in the rest of the meeting through the YouTube.
Yeah, that's the idea. If you don't have availability to see the event now,
Great,
you can
good point.
see it whenever you want. Welcome to Tobias also to the event. And
welcome to Chile as well. Did you travel?
Yeah.
Good.
So probably we should start now. Waiting for Carlos Castillo, who's the presenter. But probably we can kickstart, and during the presentation of Vicente, he can come. So, okay, I will give the introduction for Vicente now. And here we have a lot of good speakers and new professors in the Institute. And we want to give them the opportunity for get known for the community. So we are willing to know more about you guys, all of you. And for no more words, here I let you Vicente Parot, who will present all optical neurophysiology using high-speed wide area optical sectioning. So You can share your screen now and present.
Okay, so how long should I shoot for the presentation? 20 minutes is okay?
Yeah, 20, and you can go a bit further if you want. There's no problem.
Can you see the slide now?
Yes.
Title? Great. So let me see. So today I want to talk about several things I've been doing in research in the last few years. But we have a small group here, so I would like to make it hopefully something that I would like to trigger some of your interest in any of the things I'll be trying to explain. So because I have I think too much to say and I don't want to explain everything in detail. So if maybe I'll mention a few things fast, and some other things I'll go into more detail. But please stop me or ask me questions if you feel like that there's something interesting that you don't want to miss. So this is the work that I mainly did as a PhD student during my time doing my PhD at Harvard and MIT, which I did after studying electrical engineering at the Catholic University. So my main focus, I guess my research overall is trying to develop imaging techniques and measurement tools in order to study biological systems and to advance medicine. And specifically in these projects, I'll talk about applications for studying the brain. So the brain is very complex. It has many neurons, which are very small. And specifically, there are things happening at the millisecond timescale over years. And there are structures of interest that have nanometers in scale, and they span across many centimeters. So there are many different scales across which one can study the brain, both in space and time, and it's highly complex. The thought is that advancing more the knowledge that we have about how the brain works and how it stops working will hopefully help in aiding the design of new therapies and biomarkers for existing diseases, which are poorly understood in what relates to the brain. So a very brief introduction for people who are not neuroscientists, but in neurons, we have electrical oscillations which are happening very fast. The action potentials can take a few milliseconds in time, and these are propagated through the axon, where they trigger the increase in calcium concentration inside the axon terminals, releasing the neurotransmitters, which then trigger other neurons downstream through synaptic connections. This way, neurons are connected through neural networks in the brain. And in my projects in this area, I mainly focused in advancing methods for studying neurophysiology in brain slices. So this model is the brain is cut in sections, which are then preserved for the rest of the day in a physiological solution that keeps the neurons alive with the needed oxygen and nutrients. And so this means that the animal is dead, but the neurons are alive. And the special details about this model and why it has been useful for neuroscience for a long time is that it provides access to deep brain regions, and you can apply physical perturbations or pharmacology to any exposed surface. And then one characteristic is that it is very low throughput. You can only study a handful of neurons at the same time in one of these brain slices. So the goal of my project was to develop tools for large-scale optical neurophysiology. Recent optical tools have advanced neuroscience, and in particular, we can use microscopes to stimulate and record neuronal activity. And this is what I'll be showing you an example of now. So in collaboration with Sami Fari, we developed a pair of optogenetic actuator and reporter. Reporter for reporting calcium and actuator to transform light stimulation into neuronal activation. So the way this works is that when we shine, so this picture here shows the expression of these two artificially introduced proteins in a neuron in culture. And when we shine flashes of blue light, these flashes drove action potentials, which were then followed by calcium transients inside the cells. So the calcium here was reported as increases in orange fluorescence measured with a microscope. For this experiment, we also measured the changes in membrane voltage using a voltage-sensitive dye. But this pair of optogenetic actuator and reporter allows us to stimulate and record activity simultaneously. Also, we developed new microscopy tools, specifically microscope with a very large field of view of 5 millimeters and optical sectioning methods inspired in telecommunications. These optical sectioning methods were based on projecting patterns of illumination on the sample with a special characteristic of being orthogonal for neighboring locations. And together with reconstruction algorithms that we developed, the signals are analyzed to make images of the focal plane of the microscope alone, avoiding the background noise that is present in turbid tissues. So one example of how this optical sectioning method results is this is one field of view of the microscope in wide field mode. This is just a regular camera picture of the fluorescence using a lens, and then using these patterns of stimulation, we can reject the background that impedes finding details in the slices. So this in particular was important for our goals because when we express this calcium reporter in the nuclei of cells, so in these images here, each dot is one nucleus, we find that using these advanced optical sectioning methods, we are able to tell the information from neighboring cells, whereas with other previously existing methods, this information was mixed and we could not clearly record individual neurons. So using these tools, we developed an optogenetic excitability protocol to measure how the cells respond to optical stimulation. So the way this works is that we do this optical sectioning imaging for a period of 2 seconds before and after each of multiple series of pulses of blue light stimulation, which are increasing in intensity. So the results we get are that an image like this, the example here, so this spans regions of the brain, in particular the striatum and the cortex, and here in white we can see each dot is one neuron, and in red are highlighted each neuron that responded when stimulated with blue light. And so we can identify these dots as peaks in these data sets, and then extract the activity signature that they have in response to this excitability protocol. We could see that they're different in the striatum and the cortex, for example. Then if we painted with different colors according to the shapes of these responses, we could find that there are anatomically related differences, and there's a high diversity of responses between neighboring cells, and these are also distinctly separated between one cell and their neighbors. So this all indicated that we could characterize the responses of these different neurons. So one application that we used this for was to make maps of the action of drugs. And so in particular, we designed an experiment in which we measured this excitability before and after applying some drug. In our case, we used 3 different anti-epileptic drugs. And this is one example. We made a map of how the neurons respond with this drug. Specifically, this map shows in green cells that have greater inhibition by the action of this drug. So The application here is so in another example application, we studied the synaptic connectivity. And so in this optical sectioning imaging, we can see in blue and in red the optogenetic actuator and reporter. So here in this experiment specifically, we used transgenic animals to direct the actuator and the reporter proteins to different types of neurons. This means that by studying the response of the orange cells to optical stimulation of the blue cells, we could study their synaptic connection. And specifically, we measured the response to blue light stimulation in the baseline condition. And then we measured it again after applying blockers of synaptic connection. These synaptic blockers are molecular tools usually used for electrophysiology. So here we apply them and we find that there are groups of neurons. So all the neurons highlighted in green in this picture are neurons that started responding when we applied the synaptic blockers. So this could be for several different reasons, but it's consistent with a disynaptic inhibitory mechanism that has been described in cells in layer 5 of the brain cortex. So these tools also provide other possibilities for exciting applications. So the difference is that with classic electrophysiology, we can only measure one or a few neurons from a slice at each time. So it would be very difficult to find a sparse population such as these cells in green here if we don't make a map of where they are located and what's their distribution and their frequency. In any case, other applications that we envision are possible using these tools are, for example, to make maps of functional properties, like, for example, slow gradients across large areas, which could perhaps be difficult to identify if we do point-by-point measurements. Also, in cases where many neurons would need to be measured, we could screen large areas in a way that would be difficult to do using point-by-point measurements. So wrapping up this project a little bit, I want to tell you more about other projects, and I guess here I'll have to go. Well, I don't want to go into too much, as much detail as in any of them, but let's see. So I also worked with reporters of voltage of the membrane of neurons. So in the previous experiments, I was showing data about the calcium excitation of the neurons, which is relatively much slower. However, the action potentials are fast, as I mentioned at the beginning, and they can last milliseconds. And so this movie was made in the lab where I did my PhD before I worked there. And it shows the electrical propagation of an action potential through the dendrites of a neuron in culture. And this is also done with optogenetic tools that were developed in our lab. So I participated in other projects where I applied these tools for studying live animals, and specifically to observe how the correlations between the subthreshold oscillations in the activity of individual neurons was correlated between multiple neurons. And so these measurements are something that just now technology allows us to do, and in the future probably will be helpful to understand better how different animals behave and how their brains compute whatever they want to, whatever they need to behave based on their sensory inputs and their decisions. In one example of the application of these tools, I also participated in another project where I studied the integration of sensory information in layer 1 of the brain cortex of mice to see how they process different types of stimulation in order to activate neurons or produce behavioral outputs. So this also used a combination of behavioral experiments with optogenetics tools, and as I mentioned, it's another example of application of these all optical tools in combination with optogenetics. In another project I worked, so one difficulty in many of these projects is that we are measuring signals from neighboring cells, and because the brain tissue is turbid, signals tend to mix and are difficult to separate. So in one project, I worked in collaboration with Carlos Singlong, and we developed compressed sensing algorithms to further improve these optical sectioning methods. And here I have, this slide shows results of a very fast optical sectioning method. Very specifically, here in this experiment, we measured in one field of view, there were 2 neurons which were at different depths. And so when we measured placing the focal depth of the microscope at 60 microns depth, we could see that in the wide field mode, these different neurons have mixed fluorescence in the camera. And when we record their intensity, specifically when the neuron is firing action potentials stimulated by blue light in our experiment, we could see action potentials of both neurons and they are mixed. However, when we apply optical sectioning method that we developed with Carlos, then we could separate the signal from these 2 different neurons, specifically not just separate the signal from the neurons, but specifically to make an image of the fluorescence that came from this focal depth in particular, and also improving the contrast of the membrane, which is the one that generates the voltage signals. So these are all these methods were all applied to advance these possibilities in neuroscience measurements. I think we still have a little bit of time, so I want to mention another project which was not specifically focused in computational imaging, but was more hardware engineering. And I can tell you that there's a current need for fast measurements. So there are many different neuroscience experiments that have been advanced in the last few years because of large-scale measurement techniques. These have been widely applied to calcium transients, which take less than a second. However, for voltage measurements that take a millisecond, the scale is not as nearly as large yet. So in my project, I was in another project, I was concentrated in developing a method that allows for large-scale recording of very fast neuronal activity and also stimulation of optogenetic optogenetic targeting of neuronal stimulation with very fast and a large speed. So what do I mean by fast and large speed? In the recent years, there have been also many measurement methods that are already very fast. In fact, 3 papers that are called kilohertz recording of something. They use different techniques to parallelize standard measurements, and they achieve very fast point measurements. However, the optogenic stimulation can still not be targeted to many cells with a fast resolution and targeted precision. So with a team of people, we developed a new scanning method, which is a hybrid scanning that uses a moving mirror and also holographic patterns to target individual laser pulses of a femtosecond laser. And so to illustrate this, I can show you that we used a femtosecond laser with a 500 kilohertz repetition rate. And we synchronized the scanning system with this laser. So we could measure the fluorescence that came from the detection of every pulse in the laser. And then by applying different holographic patterns, we could direct or switch each one of the laser pulses individually. So then we applied this to make images in large areas. In this example in particular, this image made of 500 points was scanned in 1 millisecond. So the idea here is that this system will allow the recording of neurological signals in 1,000 neurons 1,000 times per second. And to demonstrate how we can measure physiological signals using this, we did a smaller scale measurements using the same targeting system. We measured the synaptic release of glutamate in the hippocampus stimulated by electrical activity. And so in this experiment, we used this microscope to record one point where a neuron was expressing a glutamate reporter. And then we saw how the fluorescence increased in correlation with electrical stimulation that we applied to an upstream neuron in a different region of the hippocampus. So here, the only thing that is, nothing is moving in the sample. There's just this electrical stimulation that produces the release of glutamate and the increase in fluorescence. And specifically, we could quantify this, and we saw that on average, for each electrical stimulation, there was a fast decay of the concentration of glutamate, which is consistent with the reported details of how this hippocampal synapse works. So there's we saw the fast dynamics of glutamate release and the synaptic facilitation, meaning that each time that the same synapse is stimulated, it's a little bit easy to get it going. So in summary, I have I told you about work done in several different projects to expand the tools that exist to study neuroscience research. And this is mainly through large-scale optical sectioning that we use for one photon neurophysiology methods. And I also developed this very fast scanning method, which is kind of in the other end of the spectrum to increase the scale of the very fast membrane potential measurements that we can do in brain tissues. So with this, before finishing, I'd like to show you briefly some of the things that I've been doing in my postdoctoral work at the Massachusetts General Hospital, and also that I plan to do here at Catholic University, but mainly I've been focusing on using coherent imaging techniques for endoscopy, thinking about medical applications. So these are optical coherence tomography and also microendoscopy using multimode fibers. In the research projects that I'm starting to work on now, I'm creating a new type of microscope that is based on a new principle for 3D computational microscopy, which will allow us to record volumetric neuronal activity from behaving zebrafish. So we will integrate this into a behavioral experiment in collaboration with some of the experts in this field to try to investigate some of the mechanisms of how memories are stored in the brains of zebrafish. So if you're interested in learning more about any of these topics or computational imaging or all the data analysis that we plan to do, I invite you to, well, not to come to me, but we can talk and I can tell you more details. So I want to thank everybody who participated in all these different experiments that I told you about, including many funding sources and different people who have supported me in my work in Boston and PhD. So I'm happy to answer any questions if you have. I hope I didn't go too much over time.
It was perfect, Vicento. We have enough time. Well, as I'm the moderator, I will give myself the first question. I wanted to ask of this kind of work with optical systems, how much can we do like right now in the Catholic University or in the institute? We have the equipment to do this kind of experiments?
Well, I personally don't have any equipment yet, but yes, that's a great question. Many of these projects were highly facilitated because this work was done at Harvard, at a place where we had a lot of resources. So very specifically, I can mention maybe this fast targeting system, this scanning that I was talking about. This system specifically uses a very sophisticated laser, which is we could have it in Chile, but it's like a very it's not something that you would buy just to try out if it works or if you like it or not. It's if we have a really great reason that why we will use it for many years, then yeah, I'm sure we can buy it, but it would be difficult to do this experiment without a laser like this. Well, having said that, maybe I can correct myself. The specific version here of the single pulse holograms, those are difficult, but a similar technique could still be done for using another type of laser, which is much cheaper, and that could probably be useful for other things as well. So it's not ruled out to continue this project in Chile. However, what I'm most excited about is the whole area of computational imaging. So in the project I described using for neurophysiology, this type of microscope. So although I still, for this project, used kind of high-grade research components, the technology here is comparatively very cheap. So these are all components that we could easily get in Chile and install these different systems so we can continue similar experiments. And there would be more technological advances to work on here, as well as many neurophysiology studies that we could do. However, the most exciting part for me is all this computational imaging that I've been becoming expert on. And so that's why in my new project, I'm developing this, I mentioned this new three-dimensional computational microscope, which is really incredibly simple. There will be some difficulties associated with inventing it, but the technology is super simple, and it's all components that we would definitely have access to in Chile. So that's there's a combination. For me, part of the challenge as well is how to figure out to do useful things with the use, with the tools and resources that we will have in Chile, which of course are more limited than other places. However, many great experiments in many places are done with not because of incredible technology that is available, but because of clever integration of many things. So that's what we have to shoot for.
Excellent. Gonzalo has a question.
Yes, also I have a question. I like a lot this combination between optogenetics and imaging tools. And as a synthetic biologist, I have some question about the optogenetics tools. I really don't understand very well some of their functioning, but why do you use pulses of blue light? And why like a train of pulses instead of a big pulse of blue light?
That's a great question. I think you're referring to the excitability protocol that I explained here.
Yes.
So right. So short, brief pulses. So that in the maybe quickly first how this works for so everybody can understand the same. But here this blue stuff is a protein that sits in the membrane, which is an ion channel that is sensitive to blue light. So this is very similar to photoreceptors in our eyes, except that it has been introduced artificially to neurons of interest. And so it excites neurons by the blue light that we apply. Now, in the example here, we used very brief light pulses, like a few milliseconds only. And this allowed the precise triggering of action potentials in some cases. So we know that these action potentials that happened here with this marked with this asterisk were specifically caused by the flashes of blue light, because they have a rapid action. If we had a slow acting blue light here, perhaps we could still accumulate enough current to generate action potentials, but it would be less clear that they are specifically caused by the action of the blue light. Now, in our other protocol that I explained here, the reason why we used multiple flashes of blue light in a train of pulses was that this way we could get the neurons to fire many times. And as you may know, the calcium concentration inside neurons accumulates over time with repeated firing of action potentials. And so this here was one way to accumulate a lot of calcium inside the cells, which we measured as the difference between the period before the pulses and the period after the pulses. So that was one way to kind of maximize the output signal of our protocol, if that makes sense.
So in that sense, tools that modify, for example, the pulse response of this mechanism can be useful for this kind of research?
I'm not sure I understand your question.
Like if I made an optogenetic tool that triggers at pulses on 1 millisecond and another that triggers at 2 milliseconds pulse.
Yes, that's an interesting question. There's a very highly intensive research around developing new optogenetics tools. I think the leader in this aspect is the lab of Carl Dieseroth, where they invented optogenetics, and that was around 2005. And so in the last few years, now they have developed very fast actuators, but also over the years there are many different optogenic actuators that are turned on by different colors of light, by different intensities. So in our project, we did some optimization of this optogenetic of this channel opsin, and specifically we modified the trafficking of the protein so that it would be highly concentrated in the protein in the cell membrane. This allowed using very low levels of blue light to have high activations in the neurons. And in turn, this made it compatible to use with different colors. So one general problem is that the colors in the fluorescence spectrum or in the action spectrum of channel opsins, the colors are very broad, so it's difficult to use multiple separate colors. So one obstacle we had to overcome in my project is that we had to separate these. We had to pick the most blue channel opsin and use the most red indicator of calcium, so they could be separated in the spectrum.
Thanks. And my last question is, I was intrigued about the mouse with an objective in her brain. So how that works and what are you imaging in that experiment?
So the way this works is that we implant a glass window in the, removing a piece of the skull of the animal, and then we can look into the brain, which is semi-transparent. It's not transparent, it's turbid, but we can see over some depth. Then the microscope is like pointing a camera inside this window and making a movie of the fluorescence of these protein indicators. And so in particular, the voltage indicator that we used here, which we did experiments in the hippocampus by removing a small piece of the cortex. This fluorescence here is indicates the presence of the voltage reporter that we use, and this voltage reporter changes brightness as a function of the membrane voltage. And so we could record individual action potentials differently from multiple neurons in the same field of view of the movie.
Thanks, Vicente.
Yeah, thanks for the invitation.
Okay, we have a last question from Tobias.
Sure.
Okay, if there's still time, thanks for the interesting presentation, Vicente. I'm wondering about the last comments you made about computational microscopy. That's very cool. I don't know very much about, but I'm also interested in, because I think it's very promising and can also be very cheap and very powerful. But do you have some ideas how computational microscopy can be combined with fluorescence microscopy?
Yes, sure. So right, in fact, my main interest is to implement this computational microscope using fluorescence. There are, yeah, as you implied, I guess there are many different types of computational microscopy. Some of them use coherent light, and but yeah, here this my main plan for this for the development of this microscope is to use it for neurophysiology as well, and so that would be for fluorescence imaging. But it's essentially the same apparatus that we could also use for other non-fluorescent imaging types. I may add as well, we will be designing this for a particular magnification and field of view, but it should be as easy as switching the objective to apply it also to some other range of dimensions. So this could be easily adapted to many other biological experiments if there's a need for 3D imaging with fast frame rate and high resolution.
Thanks, sounds great. I'm looking forward to an opportunity to talk about this a bit more, but we'll have that.
Of course.
Okay, thank you very much, Vicente, for your presentation. And now,
sorry, can I ask a question?
What?
If we are not starting time?
We are okay with time.
Okay, thanks.
We're with the perfect time.
Thanks a lot for your presentation. That's an amazing topic in neuroscience. Optogenetic is wonderful. I have a very quick question related with your last about the model, the zebrafish model. I understand because of the qualities of the model, you prefer to use that, but it is possible to change to another animal model, given your computational microscopy tool?
Yeah, I guess the zebrafish has been a popular model for microscopists as well, because, or I guess the microscope has been a popular tool for studying near zebrafish, because the larval zebrafish are transparent and they're also vertebrates that share many of our biological details. However, of course, you could put worms here, mice, different types of model organisms or cells, other objects. The main interest for me in the zebrafish as well, I should add, is that through a collaboration that I had the opportunity of starting at Harvard, I'm interested in developing further some of the behavioral experiments that are being developed now. Specifically, recently, basically one experiment I want to expand is to, they have been studying how the activity in some neurons persists over many seconds in the zebrafish in the brain of zebrafish. Specifically, this is because these fish in nature, they have the ability to, and the natural behavior to remain in their known territory of a river. And they do this by remembering how the bottom of the river looks and by swimming against the current. So because they prefer to stay there instead of being dragged by the current to unknown territories. So this means that they basically have some way of remembering what they're looking at the bottom. And the experiment, the behavioral experiment, has shown already that persistent activity can be measured in some of its neurons. However, that persistent activity was measured with a very slow type of microscope that can image the whole zebrafish brain. And if we expand these methods to enable faster measurements, then we would be able to measure neurotransmitters such as glutamate, like in the example that I showed before. And we could possibly resolve fast dynamics to learn more about the mechanism of how these memories are stored in fish.
Okay, we need to advance to the next presentation. Thank you.
Yes, but please ask me more questions by email, or we can schedule a time. I'm happy to answer more questions. Thanks.
Perfect. The next presenter is a guy called Carlos Castillo. He will be presenting about cardiac diffusion MRI. Whoops. Okay. So I'll be presenting, like the moderator said, about cardiac diffusion MRI. First, I want to show you a little bit of motivation about why this could be important. Cardiac microstructure is related with a lot of diseases. In particular, it's very related to infarctosomes, ischemia, hypertrophy, and fibrosis. But the problem that the heart has that other organs do not have is that it's very close, for example, to the lungs. And the lungs, as they have a lot of air, they generate some disturbance in the magnetic field of the scanner, and that is known as off-resonance effects. And in the other hand, also the heart is moving all the time. And to measure the fibers or the microstructural characteristics of the heart, we need to use a diffusion sequence. That is, the problem that it has is that it's very long in comparison to other sequences. So all of these effects start accumulating, and we need to solve them with another techniques. And from all the possible artifacts, the one that is the most important in the heart is the movement, because you cannot stop it. You can breath hold and stop the lungs moving, but you cannot stop the heart. And how do we improve the diffusion imaging in the heart? First, I did a MRI simulator. Here I just show a little bit of a result simulating a brain, but we are interested in the heart, and specifically in simulating diffusion images, as I said. So with my simulator, I can simulate this. I show here 5 diffusion images, and I can incorporate all the possible effects of the heart, like movement or non-rigid motion, and of resonance, as I said, and see the effect that it has in the fibers and the interpretation of the microstructure. And with my simulator, that is this box here, I take the normal sequence that the scanner is going to do, export some timings, then solve an optimization problem that supposedly it will fix the motion problems, and another hardware limitations that I need to put in the optimization. And then I give the scanner a TXT file with the waveform that it has to execute to do the image. So basically, I'm able to import an arbitrary waveform that is calculated by an external program and imported directly to the scanner. And I tested this. First, obviously, I need to validate it. So at the left here, I have the default sequence that the scanner does. At the center, I use my code, and I put as an input the exact waveform just to check that it gave the same results, and it did. And here at the right, I use the motion compensation. And while it looks worse with more dots and noise, this is due to the fact that for moment compensation or motion compensation, you need to decrease a parameter called the v-value. And that can be easily fixed by using a more powerful scanner. So it's not a concern, but it's something that it happens. And in hard, this trade-off of the v-value and moment compensation is more relevant, because if we acquire the image here at the left without motion compensation, basically the results are random noise. The results does not make sense. There's no coherence in the fibers or anything like that. You can see here that inside the heart where the blood is, basically, the scanner interprets this region as a region with fibers, basically. But with motion compensation, you start seeing that the blood is not interpreted as a fiber, and you see more directional results. And at the right is another type of sequence, but also motion compensated, and it shows better results with the hard, fibers. Well, now obviously it's a little bit more difficult to do things in the scanner, so I could not do any experiment with patients, and I did it with a bottle with fibers. And here the difference between these results and the previous ones is that these waveforms are a direct result of my optimization problem that I did. And I can show that the fiber directions are preserved, but obviously the results are a little bit worse because of the b-value decrease. And obviously this is, in the case of this bottle that does not move, the trade-off obviously is not worth it, but in a heart, it would. And to conclude, I just want to say that I need to design the waveform in a more powerful scanner to compensate the v-value decrease, and also prepare with my simulator to optimize sequence parameters for in vivo imaging when it's possible. And that's my presentation. There's questions. Gabriela, you have the...
No, sorry, that's okay. Well, my question is, well, thanks for your presentation, but I didn't get what does it mean, the v-value.
Okay, so the v-value is a number that is proportional to the amount of diffusion weighting of the image. So let's say if the v-value is 800 compared to 200, that means that the fibers will be sharper. Let's say it like that. So a loss in v-value results in this that you can see here, that is basically less quality in the fibers. But it's not something that is unfixable. If we scan it with a more powerful scanner, we can put a higher magnetic field and the v-value increases. So maybe that way we don't lose that much. Gonzalo, you have the hand?
Yes, I want to know, how do you build the simulator? That's very cool. And I'm thinking at, like, as we thought before, like we discussed, in use machine learning and this kind of tools to train stuff. So in this sense, have a simulation can, I don't know, create synthetic data to input in an algorithm and train it, and then use it with real patients. So can you explain more about the simulator and how it works?
Yes, well, I didn't, because of the time, I didn't explain it, but this simulator is trying to replicate the Bloch equation. That is basically the equation that governs magnetic resonance imaging. And it's currently simulating a lot of interesting properties like T2, T1 decay of that are properties of the tissue, and some diffusion properties. And yes, you're correct. By doing that, you can, for example, generate data to train deep learning or machine learning models. And that's also the idea to do it, because in this simulator, I have complete control of the sequence or what is being simulated. So I can feed a machine learning model, for example, to tell me what sequence I need to do. For example, if I want some more contrast in this type of microstructure or something like that. So yeah, that's exactly the point why it's useful to have a simulator, because now I have the tools to generate data, and basically if I have a problem, I can train a model.
Another question that I have is, I don't understand very well from the next image, like in vivo results, what means colors, and I think, no, I think one more, the one of in vivo, that one. You have some bars with colors and directions. So what does that mean? What means the direction? What means the color?
Okay, so the direction and the color is the same, basically. If, for example, if the fiber is going up, is green. If it's going sideways, is red. If it's going in between, it's a combination of green and red. It's just another way of representing the fiber directions. So for example, here, all the fibers are going like to the top right. So they are all like, I don't know, orange, something like that. And it's exactly the same here. The red regions are the fibers going like in the x-axis. The green regions are the one going the y-axis, and the blue regions are going like through the plane, the z-axis.
So with your algorithm, you want to extract maybe some kind of ordered pattern of fibers, right? Like to don't get random noise of directions, but to get a coherent pattern of fibers, right?
Yes. Yes.
Okay.
And not only the fibers, but some characteristic of the microstructure. For example, I don't know, the cell diameter or something like that.
Okay, thanks. Really interesting.
Francisco?
Yes, so I great presentation. So I have a question. So these measurements that you're showing just in this slide, so you're not doing any post-processing, right? Because you could like try to make the fibers coherent so they don't change abruptly from point to point, right?
Yes,
Or,
exactly. This is
so,
raw data.
But is that something that people do, or they just report, or that they take into account where when they develop these kind of methods that, I mean, your fibers cannot change abruptly or something like that?
That is something that could be done in post-processing. But yeah, some people do that, like put like a regularization term that the fibers that are next to each other don't change that much. You could do that, but the focus of at least of my work is to like give you the best information that you can, and then you can post-process whatever with the algorithm you want.
Okay, perfect.
Okay. Well, the next presenter is Rocío Artigas. She's also a PhD student, and I think we are good with time. So if you have your slides, you can start, Rocío.
Okay. Do you see the presentation?
Yes.
Okay, thanks for the invitation. Now I'm going to present a previous work. It's a meta-analysis that I'm going to continue the study of this topic during my thesis in the institute, and it's called the DNA methylation signatures of adverse childhood experiences, the first according to adulthood stages. Is an accepted paper until now that I wrote with my CUIDA team. This is the Abuse and Early Adversity Research Center of the Catholic University. Regarding the adverse childhood experiences, or ACE, they are associated with chronic diseases development and decrease in life expectancy. But until now, no ACE biomarkers have been identified. As we can see in the figure, it is demonstrated that during life, the flexibility of the epigenetic changes decreases with age, but we don't have until now epigenetic biomarker. Epigenetic groups the different regulations that suffers the genome, and in particular, metylomic epigenetic reactions are discussed in this paper. Metylomic blocks the different genes of the genome. So the protein that had to be synthesized from those genes is blocked. So this meta-analysis began with the selection of the databases for the analysis. We selected two different databases after reviewing 26 data sets. One of these databases is a metylomic one that is the Discovery Library. We had their available raw data and CTQ score, that is an indicator of abuse. And then as a validation library, we selected a transcriptomic database because the metylomic changes, as I said, blocks genes. So those genes blocked in the metylomic arrays must be not expressed in the transcriptomic one that we used as validation library. So in a first principal component analysis, we noticed that some cases tend to group together, especially those in blue or green, representing ages from 40 to 49 years old. So we decided to analyze, to look within the different age groups for the analysis. The analysis were, in summary, three different analyses. The first one was differential methylation analysis, from which we obtained the differential methylated sites of the genome. Then a differential expression analysis, where we obtained the differential expressed genes of the genome. And then we crossed the two first analyses to see, to validate those dysregulated genes, look into the overlapping group. So as the principal results of this study, we have that the differential methylated site, or DMC, increases with age, especially the hypomethylated sites, as we can see in the figure. In younger ages, we have under 200 DMCs, while in ages over 40 years old, we have over 1,000 DMCs. And the hypomethylated regions are the ones that increase the most, as we can see in green. According to the above, the differential expressed genes, especially the overexpressed genes, increase with age. More than 1,500 and 1,900 differential expressed genes were obtained in ages between 40 and 49 and over 50 years old, respectively. So, as I said, those hypermethylated genes in the first cohort are blocked in the second cohort. So we have we have more overexpressed genes that downregulated genes. And the third important result is that 34 genes resulted hypomethylated in the discovery library and overexpressed in the validation library over the within the 50 years old group, as the table shows. And moreover, 4 of these genes were also validated in the group between 40 and 49 years old. So, as a principal conclusion of the study, the current findings suggest that the age-dependent epigenetic effector phase, providing an eventual window for therapeutic interventions before the epigenetic plasticity is lost, I mean before 40 years old. As discussion, we need further investigation to identify the functional effects of ACE, especially in brain tissue. So as a future work, we propose that this result could be validated in a Chilean cohort, including human brain MRS or MRI studies. For this reason, I am learning spectroscopy with Professor Paulina Razabal, so we will be able to obtain the different spectrum from the Chilean population and to see the concentration of the different metabolites in the brain tissue. For example, NAA, that is a biomarker of the neuronal activity, and creatinine, that is a biomarker of the metabolism inside the brain. So we will be able to describe if those adverse events are affecting which one of these metabolites are affected at, and if they are over the normal concentrations or under the normal concentrations because of the effect of adverse events. So this will be my future work, and thank you very much for your time.
Thank you, Rocío. We have questions in the chat? No? Gonzalo.
Hi, Rocío. Thanks for your presentation. That's very cool. I get motivated by this combination of proton magnetic resonance and spectroscopic signal. Like, do you take images on the brain and you can infer chemical composition? That's the aim
of the spectroscopy study?
Yes.
The objective is to obtain the concentration of each one of the metabolites within the tissue of interest.
Okay.
So,
and also, with this technique, what do you expect?
The thing is that in several pathologies, the spectrum is already studied. So, you know, for example, if you have to, in diabetes or an hepatic disease, you know which one of the metabolites will be over the normal concentrations and which one will be under the normal concentrations. But here we don't know which is the effect of adverse events in the brain metabolites. So we want to identify that and eventually link that future results with the epigenetic effect of the adverse events.
Thanks, Rocio.
We are a little bit past the time, so maybe one last question if someone has. If not, we will advance to the next presentation. Okay. Well, thank you again, Rocio. We'll go to the next presenter, Francisco Sali, Assistant Professor of the Institute. So please, Francisco, if you can put your slides, you can start now.
1 second. Okay. So can you see the slides?
Yes.
Okay, great. So thanks for the invitation. So today I'm gonna give a bit of an overview of my research interests, and so hopefully we can see if we can work on something together. So please feel free to interrupt me if you have any questions during the presentation. So the title of my talk is Physics-Informed Neural Networks for Cardiac Activation Mapping. And I wanted to start first explaining a little bit what I mean by physics-informed neural networks, or in more general, physics-informed machine learning. So in the simplest way to understand this is in supervised machine learning, where we have an input of features that we would like to map to an output y. So we will try to learn this function f of x that will give us y. So, and a lot of the success of machine learning applications relies on that we have a lot of data available. So for example, here we have a neural network that detects if you have a disease based on an X-ray of your chest, and that could be the results of this network are even better than trained radiologists. But they use around 300,000 images, labeled images. So, but there are some other cases where we don't have that much data available. Typically, when we do experiments, we don't do 300,000 experiments. We only can afford to do 10, maybe 100. So, but sometimes we know a lot about the physics of the problem. So we have a model, like Carlos just showed. He has a model, so he knows how MRI works, so he can predict what's going on. So the idea of physics-informed machine learning is that we can combine the data that we have with some physical model. So in the other end of the spectrum, we could also have just a model, and we cannot do any experiments. So that will be, for example, the case of molecular dynamics, where doing experiments is really, really expensive, and maybe sometimes it's even impossible. So we would like to move into this yellow zone, where we can include some physical knowledge with some data to make better predictions. And we can do this in a couple of ways that I'm gonna briefly present. So we can treat our model as a black box that we don't intervene, that is just a computer code that we put some parameters as input, and it will give us some output. And then what we will do is we will run this model many times, and then we will train a machine learning algorithm to replace this physical model. And we can do this to make prediction faster. This is called surrogate modeling. When our model takes a lot of time to run, we can train a machine learning model to replace the model, to do it faster. We can also do it to calibrate the model parameters, to do uncertainty quantification, or sensitivity analysis if we have uncertain inputs. And we could also train a machine learning algorithm to go from the output to the input. So we could reverse our model. So let's say, taking again Carlos' example, we could train a model that goes from a fiber image, from an MRI image back to the fibers, if we wanted to do that. And this is also possible, but typically this requires a lot of runs of the model, which can be very expensive. So another approach is to have an intrusive approach where we will actually code our physical model into our machine learning algorithm. So we will have to translate our model into some code that a machine learning language can understand. And for example, we could have a neural network here that given some inputs predicts some output, and that output needs to satisfy a physical model, and also some needs to look like the data that we have acquired. And we can also do the model inversion approach with this method, where we will code the physical model into our machine learning language. And so it can learn the inverse model that goes from the output to the input. So each of these approaches have some advantages and disadvantages. So one disadvantage of the intrusive model is that we typically need to rewrite our model, so it can be differentiated, so it can be trained by the machine learning algorithms for training, but it has some advantages in terms of the inverse problem that classical inverse problem techniques cannot cope with. And also sometimes we are not exactly sure if our model is exactly satisfied, and we can do this in a weaker way. So we can say, I believe that my model is kind of approximate, but it will not be the exact reality. So we can also do that. And then some advantages of the non-intrusive approach is that we don't need to adapt our model, we just need to run it. But some problems is that typically we need to define previously an input space that we're interested in, but we don't know what that input space is, because we don't know how the output looks like for that input space before we run it. And sometimes we don't know if our machine learning method, if we're interpolating between points, we are not, if the model is exactly satisfied. Okay, so I wanted to show you an example of these methods in cardiac electrophysiology. So what you're seeing here is a left atrium, and we have electrical waves that propagate in the heart. So here the red means, the red colors means that the wave is propagating, so the tissue is activated, and that will correspond when the tissue is contracting. And to diagnose and to learn how to perform certain procedures for atrial fibrillation, physicians actually put a catheter inside the atria, and they record the time that the wave passes through a point. So for example, if we place the catheter here, and it will record now, just when the red wave passed through that catheter. And they basically record an electrical signal, and it has like a signature that they can record. And they start moving the catheter around until they can create an activation map of the entire atria. And here you can see they're actually guided by a 3D system, so they know where they're putting the catheter and they can cover the entire space. And so this is a synthetic map, but this is what they are interested in. So they want to create a map where, if for all the atria, I can tell where what is the activation time. So what is the time that the red wave reach that point. Okay, so what we did here is that we assume that the physician is acquiring some measurements, but what we know about this is that these activation times, or actually any traveling wave, must be subjected to the aconal equation. And the aconal equation is here and looks like this. It basically tells us that the gradient of the activation times, the norm of the gradient of the activation times multiplied by the conduction velocity has to be equal to 1. So what we did is we place a neural network that predicts the activation times, and another neural network that predicts the conduction velocity, because the conduction velocity can change in the atria. It could go faster or slower depending if we have, for example, fibrosis. We would expect that the electrical wave will travel slower, and we want to identify those points. So that's why we also let the conduction velocity vary in space. So, and here are more the mathematical details. So as I just said, the activation times need to satisfy this aconal equation. So what we do is that we write this equation in a residual form. That means that it must be equal to 0. Then we represent the activation times and the conduction velocity with neural networks. We also limit the maximum value that the conduction velocity can have, because in normal, I mean, not even in normal, in disease conditions, it cannot go above a certain value that could be something around 2 meters per second. So we can limit that, and then we construct a loss function. So this loss function will tell the neural networks how they should behave. So the first term here is minimizing the difference between the predicted activation times and the measured activation times. So if these two are really close together, so if these two have the same value, we will be minimizing this loss function, and then it will be minimizing the residual term, so which is this term over here that contains the aconal equation. So if we minimize this term, the output of the neural nets will be will satisfy the aconal equation. And then we have some regularization terms. So we have a total variation regularization term for the conduction velocity. And what this does is that it tells the conduction velocity to stay kind of constant, but it can still have jumps. But we want to be like piecewise constant, and that's what we are encouraging with this regularization term. And the other one is there for statistical reasons that I will explain later. So here we have an example in 2 dimensions. It's a pretty simple example. So I created a field that I know that satisfies the aconal equation. And you can see here that we have in the bottom row is the conduction velocity, and we have 2 distinct zones of conduction velocity. So we would like our neural net to try to learn this discontinuity in conduction velocity, but also approximate very well the activation times. So the dots are the data that we give to the algorithm, and then we train it to try to approximate it. And you can see that the activation times look very good for the physics-informed neural network, and they look okay for a plain neural network. And then if we do Gaussian process regression, it doesn't look that great, but it still looks good. And for just piecewise linear interpolation, it looks even worse. But the difference actually comes when we look at the conduction velocities. So here we can see that the physics-informed neural net was able to recognize this slower conduction velocity region, and the other ones failed, and they detected some slower conduction velocity regions that actually aren't there. So if we take a look at this cross section, so a line that goes diagonally here, and we plot the activation times, we can see that both neural nets actually do a pretty good job getting this sharp break in the activation times. And for example, the Gaussian process regression fails pretty badly at doing this because we're telling the Gaussian process to be really smooth, and it cannot capture these discontinuities. And the piecewise linear interpolation depends quite a lot on the dots that we have. But then if we look at the inverse of the conduction velocity, just 1 over conduction velocity, we can see that the physics-informed neural net has the best response. And the other ones fail, especially at the discontinuity. And I'm plotting here 1 over the conduction velocity. So if 1 over the conduction velocity goes to 0, that will mean that the conduction velocity goes to infinity. So this is a pretty bad mistake to make. So then we applied this to, so then we did some uncertainty quantification with this. And the idea here, I'm not going to go into all the details, but basically what we do is that we train multiple neural networks, and we have a good reason to believe that if we train multiple neural networks, that will give us a good indication of the uncertainty that we have. So basically here we fix some neural network with we fix some parameters of the neural net, and then we train some other parameters of the neural net, and then we end up with multiple estimations of the response. So we can build a probability distribution for our response. So we now, for every input, we will have multiple responses, and we can tell how sure we are about that result. So for example, here, pretty much all the neural networks predict the same, but if we go further away, we can see that we have like a huge range, and there will not be so confident about our prediction. And what we saw here is that basically we wanted to compute the entropy of the posterior distribution, and the entropy will basically mean how much information we have about that particular point. So if we have very little, so if the entropy is very negative, that will mean that we have a lot of information about that point. And if it's a high number, that will mean that we know very little about it. So here we are using 10 neural networks to estimate the entropy, 30 neural networks to estimate the entropy, and then 100. And what is interesting here is that we can pretty much train 100 neural networks using only 4 times the resources that if we train just one. So the cost of training 100 neural nets is only 4 times the cost of training just one. And then we see that the error to estimate the entropy starts decreasing, but with 30 neural nets, we have kind of like an elbow pattern, and we decided to go with 30 neural networks there. Another interesting thing is that, let's say that we have these points. Here we have 30 points, and then we compute our prediction, that we compute the entropy. And the premise here is that we don't have much information, so the entropy is high. We also think that the error will be really high. And it tends to correlate. So the idea here is that we can do active learning. So start with a number of samples and then place the next sample. So move the catheter to the point where I know the least, where I have the least information, and that will be the point of maximum entropy. And the hope is that that will reduce the error of my predictions. So here's the active learning algorithm that I'm not going to go into too much detail, but here you can see that we start with 10 samples and then we do active learning, and the error decreases quite fast. And after around 20 samples, it gets stuck in around the same value. So this is for the 2D example that I just showed. And if we compare this with the random allocation of the points, we always get better results with the active learning, for both activation time and conduction velocity. So here's how the active learning looks in 3D. So you will see points appearing, and that will mean where the physician puts the catheter. I mean, where we would tell them to put the catheter. And you can see how the estimation is improving. But actually, after a couple of points, it doesn't change that much. So it stabilizes around some solution. And here we have snapshots of what I just showed. And you can see that with very few points, I believe this is like 10 points, we get a fairly good result. This is the ground truth, the last column. And with 0.25 samples, we get, they look very similar, right? And then we are just pretty much confirming the results. We also did this for a case where we have a reduced conduction velocity in part of the atria, and it looks, and the results are pretty much the same. And here are the formal results, and we see the same pattern, that we can decrease the activation time. So I believe I had 20 minutes, so I don't want to take more of your time, but this was another application that we're working on in microscopy, where we had a physical model of the images. So just to conclude, so physics-informed machine learning, we can combine data with mathematical models to improve our predictions. And when we can do this intrusive approach, we can solve inverse problems in some ways that are not possible with traditional methods. And also we can do uncertainty quantification very efficiently. We can do active learning, and we can learn something that we don't observe directly, for example, like the conduction velocity in this case. Okay. So that was my presentation. I don't know if you have any questions.
I have a question. Can I? Oh.
Yes.
Thanks. Thank you for your presentation. I wanted to ask, could you explain a little bit more about this, about the application of mapping the propagation in the heart? Basically, why do we need this, or what is it used for?
Yeah, so basically they try to identify targets to perform an ablation. So usually they will try to see if there are any bits coming from regions that are not supposed to be producing bits in the heart. So they are called ectopic bits, and they try to identify where these are coming, and then they will ablate them. That pretty much means that they burn that piece of tissue. So they don't, it stops producing these ectopic bits that can trigger arrhythmias.
So do you think the models and the advanced physics-informed machine learning will help in deciding what places should be measured to get the data, or you think it would help to decide where to ablate?
Yeah, so we are focused just on making the best map and with the least possible samples. So that the idea here is that if you need less samples, you can do it faster, pretty much. And also if we can provide some uncertainty that that can tell the physicians, measure there, because we're not really sure if that's of what we're seeing. But we're also working on some projects that will tell us where to ablate, but that's related, but not completely. No, it's not directly related to this.
Thank you.
Gonzalo has a question.
Yeah, I'm really interesting on machine learning and artificial intelligence. So I get intrigued first for the eikonal equation for traveling waves.
Yep.
That I found interesting how it works with traveling waves, because I have been working in traveling waves of gene expression, for example. So I want to know if in the eikonal you have voltage. I think so.
No, it's like a general equation. So you can abstract any wave as something that is traveling, and that it will arrive at certain points at certain time, right? So for example, I got an email yesterday from someone who was working on seismic applications, and there you have, like, I don't know the exact name in English, but I believe it's the epicenter, and then you will have the earthquake will get to different locations at different times. So you can, instead of modeling directly how the ground is moving and everything, you can just say, well, this is a wave that started somewhere and is arriving at some point at different places. So you can, it's a very general approach. It's like a simpler model for traveling waves.
Great. I will take a look on that equation, and also ask you about what do you think, or your opinions on inverse problem solving machine learning algorithms? For example, I seen at some time a machine learning algorithm that solves partial differential equations, and I found it really interesting. So you know more about the field. So what are your expectations, and what do you think about that?
Yeah. With the approach that I just showed, so let's say that I just give you one point where I know the activation time, I could also solve the partial differential equation, which is the eikonal equation. So this is an approach that could also be used to solve partial differential equations, but they are typically not really either accurate or fast. So if you try to solve a partial differential equation, it will take, like, I don't know, maybe 100 times more than solving it with a traditional solver. And it could also not be that accurate. But if you have some data, like the case that we have here, and you want to do an inverse problem, then they become a better tool. Because then everything that you do with a traditional PDE solver is a bit more tricky, and taking the gradients is really tricky. So for those kind of problems where you have a PDE and you have some points that you know where the solution is, that is when these approaches are really good. yeah, and I mean, and there are also like many approaches. So it's hard to cover them all, but I would say that the problems that it applies where you have a little bit of data, or even like a full field of data where you have like a complete image where you know the solution, and then you want to invert the model. Those approaches also work really well. You need to have some data in summary.
And in a graph, a plot that you show, if you can go back in the slides, maybe I can stop you in the one that has root mean square error and mean square mean absolute error.
Okay. Yeah,
so how those metrics are interconnected? Is a guion or is a minus?
No, so root mean square error is that you take all the terms, so the difference between the predicted and the real value, you take the square of that, and you sum them all, and then you take the square root. The other one is just the absolute value of that, it's the absolute value of the difference, and then you take the average of that. So actually in both you take the average. So they are not the same, and the reason why we didn't use the same metric is because in conduction velocity, some methods tend to like what I showed here. Yeah, here is that some methods will produce like near infinite values for conduction velocity. So here I'm plotting 1 over conduction velocity. So this will be like a really high value. And if you have a mean squared error, that will get super penalized because you're taking the square of a really large value. But if you use the mean absolute error, that it works. I mean, it's more representative of what is actually happening.
Okay, so so the root mean square error penalize more the outliers, right?
Yeah, exactly.
And how do you combine these two metrics?
No, so these are just after testing, and so these are just post-processing. So during training, I just penalize the mean squared error. So yeah, so here I have 2 mean square error losses. No, I am not doing the. I mean, you could do it, but it's not. Sometimes it works well. Depends how close you are to 0, because you use something like mean absolute error for your loss, and you're close to 0, you have a discontinuity, so it doesn't work very well.
Okay, thanks. I like a lot this presentation and the use of these novel tools and machine learning tools to extract information from biology.
Yeah. So I teach a class about this. So it's this semester, but if you guys are interested, I will be teaching it again next second semester, and you'll probably have a IBM code, so it should fit in your programs.
Great.
Gabriela has
the name of that class is? Sorry?
Should be Physics for Machine Learning. But it's still, I mean, it still doesn't exist as an IBM class. Now for bureaucratic reasons, it doesn't exist.
Okay, but for learning, it's still there is.
What do you mean?
No, I mean that we can still go just to learn, not to take it.
Oh yeah. So I mean, if you wanna like go as a just to hear about the class, you can send me an email, and I can add you to the Canvas page.
Great, thank you.
Gabriela.
Yes. So Francisco, thanks a lot for your presentation. I have a particular question that you said that you don't want to go deeper, but since I started to work with uncertainty and model inversion, so I wanted to know how you manage the posterior probability.
Oh yeah. Yeah, I mean, I'm happy to answer that, but it's kind of a long answer. Yeah, so I mean, basically, No, I mean, I can explain. So basically doing uncertainty quantification with neural networks is super tricky. And there are like many proposed methods and there's a lot of controversies. But one method that seems to work very well is to train multiple neural networks at the same time with the same data or some corrupted version of the data. So what we did here is that basically we sample some parameters of the network and with a normal distribution, and then we fix them. And then we also have another neural network that we train. And so this will be the network with fixed parameters will be our prior. So these are our prior functions. And then we have on top another net that we can train. And then we train these two networks together, but we don't touch the parameters of this network. And that will give us one posterior sample for every input pretty much. And then we can do this 30 times or 100 times, and that will give us some uncertainty. And the concept is called randomized prior functions. And we have used it a couple of times, but there are some papers coming out now that even say that you don't need this prior network, and you can just train multiple networks, and that should still be a good estimation of uncertainty. And in practice, we have seen that it behaves pretty okay. And the problem is that you need to train multiple networks, and that is not for free. But if you write everything in a tensorized way, it can actually be pretty cheap, as I just showed. So here training 30 neural networks, that's what we use for pretty much everything, all this work. It only took like 2 times the time that it will take for just to train one neural network.
Excellent.
Can I interrupt here? And why is this? Why it takes less time to train them?
Because what you do is that you write everything. So let's say in a one neural network, you have these matrix vector multiplications, but you can define a 3-dimensional tensor. So you stack all your networks in another direction, and then you stack all your inputs in another direction. And then if you want to do this operation in a vectorized way, it's super efficient. So that's why it doesn't take the same time to train. That's why it's not proportional.
Okay, so it's like a parallel training.
Yeah,
or
kind of.
Not.
It's not even, yeah. I mean, but it's not that I'm using different cores to do this. I mean, it's just that I'm.
It's all in one, for example.
It's like, I mean, it's like a super efficient. It's an operation that is super efficient to do in the computer. So it doesn't scale with the number of networks that you have.
Okay, thanks.
Yeah.
I have a last question that's related with active learning.
Yeah.
Is there another the trade-off between exploring and exploding?
Yeah.
When you ask to act, like to how you manage that?
Yeah, so the entropy should include those two. Yeah, I mean, typically you need to put those two terms explicitly, but what we have seen is that the entropy works really well in these cases. But there are definitely some better things that you could do. And there's like a whole field that works on that. But the entropy should balance those two things.
Okay.
Yeah.
And the entropy is channel entropy, right? It's information entropy.
Yeah.
Okay.
Okay. Thank you very much, Francisco.
So I have to run to another meeting. We have
no problem.
It was great talking to you. And if you have any more questions, just send me an email.
Perfect. Okay. Thank you again, Francisco. We'll start with the next presentation from Carlos Vidal.
Hello, everyone. Can you hear me?
Yes.
Yes.
Great. I'm going to share my screen. Okay. I want to present you a tool that we have developed at the laboratory of Dr. Raj, led by Guillermo Yañez, to inform the learn phase from the design, build, test, learn cycle for engineered synthetic genetic circuits about huge volumes of data. It needs to be filtered, collated, and analyzed, making tools that manage this task an important resource to close this cycle. Flapjack is such a tool. Implemented as a web app, the front end provides querying, plotting, and analysis tools, and a REST API and Python package are provided for full integration with external build and learn software. We demonstrated that Flapjack closes the gap between the build and learn phases. It uses a microservice architecture via Docker virtualization. The backend engine was developed using Django, thus supporting many Python tools, especially for data analysis. Our approach could decrease time-consuming and error-prone data wrangling. It can also significantly enhance data sharing, management, and analysis for synthetic and system biology. We invite you to use our new tool, available at flapjack.raj-lab.org. Every feedback is welcome. We think you're gonna love it. Thank you.
Yes, Carlos. Thanks. So I want to make the first question, and this is about data management, right? And these are tools that we are developing with in the synthetic biology lab with Team Raj, and we have a lot of now software tools that help us as scientists to reach better results. So Flapjack is one of these tools. How do you think other fields can use this tool also? Because this is also kind of data management in the whole spectrum, but is oriented to synthetic biology. But other fields also use fluorescence measurements. So how do you think this tool can impact first synthetic biology and system biology, and how it will impact other fields, like in future?
Well, in system biology, it's going to impact in a way that it's going to make easier to have the model of design, build, test, and learn cycle. And because you now can have many iterations of a sample, and you can see and have and you can see it and know if that's going to work, or you have to make some adjustment and correct your experiment. I think in the other areas, there are not mainly think about improving some system, but it doesn't mean that they cannot use this tool. They can use it to have an easier way to plot their data, to have access and to analyze their data, and even Flapjack provides a way to share data and collaborate with other person. So it's going to make easier the workflow for laboratories, given the times more than ever, given the times that we are not able to meet with each other.
Thanks, Carlos. Thanks.
I have a question. The first one is very basic. Why it's called Flapjack?
Maybe Gonzalo can help me with that.
There is no reason. I think it's maybe because it's simple. I think maybe Tim has think on Flapjack that is an easy to prepare dessert, like and because this make data simpler, he put it Flapjack.
Okay, so it doesn't have any relationship with the biology or something like that.
No, I think it's just for simplicity, because you have, well, for example, when we work with different data sources, they're not in the same format, nor have the same measurements, nor anything, right? So you need to wrangle with this data in order to fit in one model or method or pipeline. So what does Flapjack basically is structure data in a manner that is understandable by a lot of tools and algorithms, and also use a data format that I don't remember the name, but it's like tidy format that allows you to manage in a more flexible way. So I think those are the pros. You have data in an structured way, and you have access to a lot of software tools to analyze it, and you have inbuilt analysis tools.
And this is mainly used in fluoroscopy, or in what's the input of this software, and what's the output in the, for example, in the web page, if I go there and I upload my data?
Well, you can upload data directly from it's fluorescent data from a plate reader, and you're going to get a plot. You have options to characterize your data, and you're going to have access to this plot that you can already download it in a paper format, for example.
Also, I want to add to that we have image analysis also. We have like pictures of colonies with fluorescence, and that's also an input to this system. So we are expanding like the range of tools that export that are compatible with Flapjack. So we have plate readers so far, and imaging tools, and those are imported to the data structure of Flapjack. So any suggestions of data format that we should support are welcome.
Maybe an Excel format or something like that.
But for example,
yeah, I don't know if I can show you, but you actually just upload the Excel file that you get from the plate reader. Then you are prompted in the interface to put some data to complement that data. But basically, you just need to add a few things to the Excel that is provided to you by the plate reader.
Yeah, I think basically this pipeline automates the workflow on synthetic biology, at least when we put samples on a plate reader or equipment and we obtain signals, we measure those signals to get data, right? And that data could be in different formats, and this unifies the format, like reads the Excel sheet that gives you the equipment and structure everything in a new format that is the Flapjack data structure. So then you will have a lot different data sources that will be in the same data structure, so you can compare easily between experiments and different results on different labs.
Perfect. Any more questions? If not, I think it's time for the lunch break. Right, Gonzalo?
Yes.
It's until 2 p.m. So you need to eat fast. No. Well, yeah.
Okay.
Let's start the stream until the next block.
Okay.
Great. See us.
See you guys. Hi, hi.
Hi. So we are in a couple of minutes to initialize the last block of this activity. Hope every one of us has a nice lunch. Okay, so we're waiting to Tobias. Okay, so Tobias has just written to us that he's a little bit late because of a faculty meeting.
Maybe I can start then and do the same that we do with Martin.
Okay, that's great. So now we will switch and we now we present Gonzalo Vidal. He's a PhD student at the IIBM Católica. He works in the synthetic biological and complexity lab of the lab. And he will be presenting his posters for logical operations for intelligent cell algorithms.
Thanks, Gabi, for that introduction. So here we present my research and what I want to do, what I have done so far, and my goal. My general goal is to go through from code, software code or computational code, to DNA code in order to compile algorithms in DNA in order to run them in biological substrates. So in synthetic biology, predicting the behavior of secreted components in their host is a central goal. And the design, build, test, learn cycle is central to engineering disciplines, and tools to accelerate it are necessary. In this poster, I will show you Loica, that is a software tool that accelerates and connects design and build stages. So Loica is basically a Python package built with objects-oriented programming, and these objects interact with each other to make the model. Then we have, and this package will be stored in Pipey to be available under pip install, which is the common way that we Python users install packages. And this software will be also available in GitHub and is oriented to an open software development. So the aim is to raise a community that develop this software and not be the only one developing it. So that's basically the first part of the project. The other part is build high throughput open scientific hardware. So here I will show you one expected results. So basically in the design, build, test, learn cycle in synthetic biology, we has the DNA, we start with DNA. We use that DNA to transform cells. The transformed cells emit a signal, which we capture with scientific equipment like microscope, plate reader, and other techniques. And that gives measurements that give rise to data, and data gives information to software tools, as well as models compiled as algorithms. The software tools that we use are Loica, that focuses on design build stages, and Flapjack, that focuses on test learn stages. These software tools output a protocol that is human and machine readable for robots to assemble DNA. And with that DNA, you start the cycle again. So basically you design DNA to make a desired function in cell. You measure that function and compare with your model and see if you can adjust the model or design new behaviors or functions on cells. So that's basically what we want to do here. And for this, we develop the tools to accelerate this cycling and obtain more information per cycle in synthetic biology. So the expected results go as a novel software tool for gene circuit model and design that can output assemble instructions. So this new model, this new software tool model genetic circuit behavior in order to design it, and will output an instruction or a protocol for robots or humans to build the DNA designed in the computer. It also has a novel two-way communication with data using Flapjack. So the model is, these two software tools are interconnected to close the DVDL cycle, being one of the first models that has this really close connection to structured data. It will be also the first software that allows data to SVOL3. So recently in June, SVOL, that is the synthetic biology open language, has his third release, his third iteration. And with that, previous SVOL iterations just allow you to store genetic sequence information. And now SVOL3 iteration also allows you to store experimental data of an implementation. With this, the development, after that, I will develop a high throughput open scientific hardware for gene expression characterization that will mimics the function of a plate reader and will be made with open technologies such as 3D printer, open electronics, and laser cut acrylics. So after that, as conclusion, this research aims to develop software and hardware tools that grasp, automatize, and accelerate DVDL cycle in genetic circuit design. So the takeaway will be improvements in predictions in genetic expression will allow more reliable genetic design of cells, collectives, and organisms. In future work, I have expand the genetic models from bacteria to plant and keep improving and adding features to Leica and Flapjack. So that's basically these are the two software that we are developing. Flapjack is actually developed and is available in bioRxiv for now. The publication is pending. And Loica is in advanced state of development, but we still like data to feed the algorithms. So hopefully then when we can do experiments again, this continue and I can give you more results about that. So that's it. I will be glad to answer questions about this.
Okay, thanks, Gonzalo. So, any questions? We have Carlos Castillo.
Yeah, at least for me, it is not clear what Loica does. Can you explain it like in simple terms?
Let me explain better Loica. So I'm prepared for this. Let me look for the correct presentation to show you this stuff. I will stop share this and I will share a new presentation if I can find it. I think this is because there it is. So let me find, I have problems with PowerPoint. Okay, so Loica, how works Loica? No, sorry. I missed the presentation. Here it is. Yeah. So this is what I don't know what's happening, but it still open my another PowerPoint, which is not the one that I want to show. Let me close that to see if I can show you the correct one. Okay. So we're going to share this here. Okay. So this is basically the structure of Loica. And here we can see that Loica is a Python package, as I said before, and it generates in the interconnection between objects. The basic objects are operator and regulator. And in this relationship, it generates ordinary differential equation models for gene expression, like this one that is the representator. Okay, so the basic components are these objects that are genetic network, that is the main actuator, and encapsulates and coordinates all these other parts. The operator is an abstraction of a DNA fragment that has basically a Hill function where the expression of the output is, it maps the input into an output following a Hill function or equation. That is basically a smooth activation function. Then we have the regulator, that is the one that can be an input of the operator. That is basically the abstraction of a transcription factor. The producer is an abstraction of an enzyme, which can generate chemicals or produce chemicals. And the reporter is the abstraction of any reporter, such as fluorescent proteins or luminescence. So these are the objects that make the genetic network. Then we have an assay setup. And here we state the metabolism, which give the context of gene expression and incorporate biomass and growth rate. The sample, that is basically, if this was an experiment, the sample will be just one well on a 96 well plate. So it's only one sample, like of the many that you can have. And an assay is a collection of samples in the same experiment. And this assay, and here's how Flapjack and Loic are connected, the objects. These are the data structure of Flapjack. And here's the objects of Loica and how they are connected. So the genetic network encapsulates all these objects and feed sample as well as metabolism and a a group of samples give rise an assay. And an assay, these ones in red have two-way communication with Flapjack. So they are basically the same. The sample here is basically the same as sample in Flapjack. And a study is only in Flapjack, that is a bunch of essays with a meaning, like that want to solve a question. So basically, here's how it works. Loica, for a NOR gate, for example, I'll state the NOR gate as a genetic network and vinculate to Flapjack. Any ID is a vinculation to Flapjack. I create a reporter, add the reporter to the network, and create two supplements that are input to my NOR gate. That is the abstraction of a tandem promoter transcriptional unit with alpha, B, A, B, K, and N, which are the parameters of the Hill function here, A, B, K. So basically, when the input is infinite, for example, this will be, the output will be V, and if the input is 0, you can see that the input will, the output will be A, or similar to A. So here we have the genetic network, the reporter, and the operator that controls the output of the fluorescent protein. We make an assay, so we state the metabolism and concentrations for the samples in the assay. So you have a log space from -3 to 3 with 12 samples in between in the two concentrations of inducers here. And then you set up the assay and run it and upload it to Flapjack, just in the same code. And then in the web app of Flapjack, you can see the data that you generate using Loica here. So when the concentration of the AHL1 or signal 1 and signal 2 is low, so there is not signal 1 nor signal 2, it is high, and where is one of those is low. So this is the abstraction of the NOR gate in synthetic biology. Another example could be the represilator. So here we state the represilator genetic network vinculated to Flapjack ID and create regulators. For here we create 3 regulators like I, TET-R, and CA that they are basically transcription factors and add it to the genetic network. Also create reporters to vinculate the signals to Flapjack, and operators that control this expression. So we have 3 operators that get rise of the dynamics of the system. So one NOT gate has an input Ci, an output like I, which repress the following NOT gate has input like I, and as output at R, which repress the following NOT gate, which has input at R, and output Ci, which repress the first one. So it's a ring oscillator. And then we have gates that output basically have the same promoter here and output a different fluorescent, a different thing that in this case is a fluorescent protein. Then we create the metabolism. This is a bit simple, and we can output the behavior of this dynamical system as an oscillator or represilator in synthetic biology. So that's basically how it works Loica. You state a genetic network and create it. You set experimental conditions, and you get the data. I hope that answered the question about how it works Loica.
Yes, now I understand.
Another question?
So maybe I could ask, you now are working with cells, and you want to move to plants.
Yes.
Why that?
Why I want to move to plants is basically because my main goal is design plants that grow in Mars. So basically at this stage, I'm trying to get proficient in genetic design of simple organisms like Escherichia coli
that are faster in the DVTL cycle. Like you can make experiments from one day to the other, but in plants, you sometimes need to wait for weeks or months even to get the results. So that's basically, I start with bacteria because it's simple and less complex and allow us to iterate faster in the DVTL cycle. And when we have mature software tools, I think we will, or at least I will move to model plant systems to be able to design plants that grow in different conditions, such as Africa, such as cold conditions, hot conditions, and in less water conditions also. So that's the main goal, be able to modify bacteria, reliable modify bacteria and genetic engineer bacteria, and in future, be able to genetic engineer plants also, which is more complex. But it's just what that for the simplicity of bacteria to work.
So Carlos Valle has a question.
Yes. So Gonzalo, when you say that you want to work first with bacteria to later move to plants, is that right?
Yes.
So, how do you know, or when do you know that you are done working with bacteria, or that you have
Hello?
I don't know.
Okay, so I don't know if I will know very well when I should flip from bacteria to plant. I think that's a question for the futures Gonzalo, which in some way will say, okay, I'm proficient in genetic engineering, so in bacteria, so I should move to plant. I think I think move to plant could be something for the postdoc or something like that.
I see. Thank you.
Thank you.
Okay, so if I think the first was, we have two more questions, one from Rocio, another from Tobias. So I think Rocio was first.
Okay, Gonzalo, could this have any application in certain human pathologies, such as cancer, for example, selecting some clusters of genes, something like that?
I think this model could work as in bacteria as well as mammalian and plant models, but some modifications should be done because bacteria, because it's simple, doesn't have a lot of post transcriptional modifications, don't have methylations, for example, or different ways or mechanisms to methylate or do epigenetics. So I think in future this work can be taken by other people also and do it with mammalian or eukaryotic cells to study human stuff. And I will focus on plants in future.
Okay, thank you.
Thank you.
Yes.
Hi, Gonzalo. Thanks for the presentation. So you mentioned in the end that you would like to build some hardware that's similar to a plate reader.
Yes.
Could you tell us a little bit more about that, and why do you need to build something? So why don't you just use an off-the-shelf plate reader? What are you going to do different?
Yeah, so in the design, build, test, learn cycle, you have a gap in between the build and test. That is how you will test, what tools you have to test stuff. And one big thing that we notice here is different equipment give different signals in different ways. So one way that we found to make this DVDL cycle accessible to everyone or most people, and to provide tools that can be the same anytime across different research labs, we provide users with a hardware to extract data also. So you have these two software tools that grabs the DVTL cycle, and we also provide you a hardware
to test your designs. So that's our idea. Use and also try to mimic the plate reader, because we have a lot of data with plate readers, so we're more familiar with that. But in the project, we will see if that's what we need, because we need something that has an input, something that is common in research labs, like microplates, and the output will be flapjack information that will be in the software. So that's what we thought in something similar to plate reader, to have an input a microplate. But basically, that's the only constraint that we found so far, like be able to fit regular lab equipment or consumables, I think plate are, into the pipeline.
Thanks.
Okay, Ivan.
Okay, so thanks, Gonzalo, for your presentation. Now it's the turn of Tobias Wenzel. He's an assistant professor of Universidad Católica and head of Wenzel Lab. And he will be presenting a keynote titled Single Cell Analysis with Microfluidic Droplets.
Thank you very much for the invitation and the introduction. I'm very happy to interact with some of you basically only 2 days after I finally got to Chile. So hopefully I'll see you in person as well soon. I'm not sure how that's going to go with the lab restrictions, but I'm looking forward to that. So let me see if I can share here. Okay, so now you should. Can you see my presentation? I'm gonna make it a little bit smaller, like that. Okay, perfect. So I decided to talk to this. I actually used the template for a brief introduction about what I'm going to talk about. I am not mainly going to present my own research results, but instead I thought it would be more interesting maybe for you to tell you a little bit about this new method that I'm bringing to the Institute, this droplet microfluidics, and some very cool, powerful things that can be done with this that have been developed in last years and that have spread very fast around the globe and that are already used by, I don't know, I would say all leading research institutions. There are also commercial solutions available for some of these methods, but they're extremely expensive. And so either there are institutes that have unlimited amount of money to do this, or there are institutes that have some expertise in developing these methods so that you can do it in custom ways. So developing your own tools, making your own microfluidic chips and so on. So I would like to give you a brief introduction about some of those things. And this is about single cell analysis. So I'm working with microfluidics. I will give a brief introduction on that as well.
Can I interrupt you? Are you in full screen with your presentation? Or you are in the...
Sorry, how do I do this? Sharing is paused.
Full screen.
Bring your shared window to the front. That is strange. Yes, thanks. It's not full screen, but...
there it is.
There it is now?
Yeah, there it is. Thanks.
Okay. Thanks for letting me know. Okay, I'll just put this in the corner. Okay. There it is. So, so I'm going to talk about microfluidics, but microfluidics is very broad, actually. So there are a million different topics within microfluidics. It's like anything with liquid and that's small. So there can be many, many things. Most of them are not even biological. But there's this very interesting thing that has emerged that is particularly useful, and that is single cell analysis with microfluidic droplets. So that's what I would like to talk about today. So single cell analysis means studying cells individually with their genome, the transcriptome, the proteins that they produce, other metabolites, other molecules that they produce, and also cell-cell interactions. And this is very important because in our body or in the environment, you have a lot of different cells. And so sometimes just seeing what this whole organ does or so is not enough. So the function exists because of all the different parts playing together. So you need to understand these parts. And so single cell analysis is necessary and it's challenging. You need to analyze hundreds of thousands or millions of different cells at the same time. And that can be difficult or very expensive. So microfluidics has been a very good tool for that. And the main thing, how this works with droplets, is that you basically bring oil and water with your cells inside on a little microfluidic chip. I'll give more detail later. And then because they don't mix, you generate a lot of little droplets very fast. So this is with a ultra high speed camera. So really there's like 8,000 droplets per second that you can produce, for example. And then each of these little droplets would be one experiment. And then in my lab that's now starting at the Institute, we look at ultra high throughput experiments to study the microbiome or different bacteria that live on the human body, for example, or the environment. So I will also mention that at the end. Okay, so briefly, I have these 4 parts in my presentation. First, a little bit more detail on microfluidic droplets. Then one key example of an application, which is single cell transcriptomics in barcoded droplets. So this is relevant for eukaryotic cells. So in the human body, for example, all the cells have the same genome, all the cells have the same DNA, but then they do very different things and they look very differently. And this is because the genome is read out differently with the transcriptomics. So if you can measure in all those different cells what genes are transcribed, then you can understand more about what they're doing. So this is important for eukaryotic cells. In prokaryotic cells, so bacteria basically, bacteria do not have the same genome. So there are a lot of different bacteria in the environment. And so there we don't want to read the transcriptomics, but we want to have the genomes of the single cells. And this is very little material to start with. So it's very challenging to measure this or to sequence the whole genome of just one cell. And again, microfluidic droplets, or in this case, microgels, have turned out to be the most useful tool to do this. And then I will briefly tell you what I'm looking at in my research. So this is cell-cell interactions between bacteria and droplets. Okay, so first the microfluidic droplets. I've already said a few things about this in the same image on the previous slide. And so the key is again that you insert oil and water into a small little junction, and then they just split according to physics into these little droplets. And actually there's one little magic trick that you have to do. So this wouldn't work so well. So you would get droplets, but then they would immediately merge again when they touch each other. So you also have to use soap, basically, a surfactant that stabilizes the surface of the droplets so that they stay separately. And those are particularly developed now for microfluidics. You can buy special oils and special surfactants. And the reason that you can do, the reason that you can do single cell experiments is that you can just choose the dilution of your cells. So whatever cells these are, bacteria or eukaryotic cells, you have to dilute them before you inject them onto your chip in such a way that you have less than 1 cell per volume of a droplet, basically. So the encapsulation of those cells is random and it follows the Poisson distribution. And so depending on your input concentration, this is given here in these different graphs. I'm not going to go too much into detail now, but basically they give you the probability of having 1 or more cells in a droplet. So here, for example, this turquoise, this blue-green line, says that if you have, on average, 1 cell per volume that will end up in 1 droplet, you have the highest concentration of 1 cell per droplet. But you also have quite a lot of droplets that have more than 1 cell. So if you want to do single cell experiments, then you want to avoid having 2 or 3 cells because that will screw up your results. So what you do instead is that you use an encapsulation ratio that's much lower. So most droplets are empty. So you only have every third or every 10th droplet actually occupied with a cell. And then you can be quite sure, then it's very, very rare that you have more than one cell. So here, for example, this blue curve, you have more than 99% probability of just getting one single cell and a very low probability that you get 2 cells per droplet. So yeah, sorry, this is this way around. This is 0 cells, this is 1 cell, and then you basically have no double cells. So you can do very reliable single cell experiments where you have 1 cell in a droplet. Okay. And now I'll just very briefly, so this is a sort of brief presentation, so I will only touch on different things. And if you're interested, you can talk to me later, or you will see a different presentation of me somewhere else where I can go in more detail. But this is just a brief taste, basically, how these microfluidic chips are made. So we're currently building all these facilities with Andrea Raviaso in the Institute, so that we'll be able to make these chips ourselves in the Institute. So how these little designs are made is with photolithography. So you use a special resist, like a plastic that's sensitive to light. You coat them onto silicon wafers, and then you illuminate them with a mask that has your microfluidic chip design on it. And then you develop it similar to sort of old school analog photography. And then you get these little channels on the silicon wafer. And then you can make imprints basically of these masters. So you can make many microfluidic chips from one master. And for these imprints, you use this rubber, as you can see it here, this transparent layer on top that you can bond to glass slides. And then the area that's left between the rubber and the glass side is then the little microfluidic channel. So you can see, for example, here, this blue dye that was put into the channel, and then it fills the little chambers and channels that are in the design. So with photolithography, you can make pretty much any channel design, and then you can use that to make those droplets, for example. And this is, microfluidic droplets are very useful for a number of reasons. So you can work with single cells. You can look at interactions, which is very unique. So there are not a lot of other methods to do this. You can work on very high throughput. You can work with millions of droplets and cells in parallel. And you have very little contamination. And this is always a problem if you work with Eppendorf tubes, for example, and you just have one single cell in there. The volume is so big around it that it's very likely that you have some kind of contamination. So in these little droplets, there's very little volume together with the cell. So very little contamination possibility. And it's very versatile, as is shown in these diagrams. So with droplets, you can make droplets, but you can also put different things into the same droplet. You can incubate them on a chip. You can read out fluorescence. You can, you can incubate them in a line so that you see changes over time. But you can also incubate them in Eppendorf tubes. You can take them out of the chip and put them back. You can merge droplets, you can sort droplets, and you can add little amounts to droplets later. So you can do a lot of different experiments. And it's very reagent efficient. So you use a very little volume to make a lot of droplets. So if you're working with an expensive enzyme, for example, you can maximize the experiments you can do with your pot of money. Okay, there we go. Is this the last one? Yes. Okay, so this was my very brief introduction to what are microfluidic droplets and why are they useful. And now I come to the two main examples of single cell analysis. So the first one is about the eukaryotic cells. So again, in a tissue, in human cells, for example, or other possibilities. So one particular example that I think is very powerful in this context is cancers. So if you have a cancer biopsy, a little bit of tissue from a cancer patient, you can look at what different cells are actually in the cancer. So there might be a lot of cells that react to a certain medicine that you will give the patient, but there may be some cells that do not react to it. And you might not notice those cells initially, but then most of the cancer goes away with the medicine, but then the rest can grow back and cause a problem, for example. So it's important to know what kind of cells are in your cancer. So this could be a bit of cancer tissue, for example. And then you can isolate the cells. So there are some chemicals available that the cells detach from each other, and they're just single cells in suspension. And then with the right concentration, as I mentioned before, you can encapsulate them in droplets. Now, for this particular method, the challenge is that you need to know which cell is in which droplet afterwards, or to be more precise, you need to know which different mRNAs, which different transcribed genes all belong together to one cell. So you need to barcode the droplets. And there are a few different methods to do this. And actually the two main methods were developed at the same time, and they were published back to back in Cell in 2015. So I'm depicting the drop-seq method, which is the one that had the nicer images basically to show you, even though I prefer the in-drop method actually, but I'll briefly get to that. So in the drop-seq method, they use little beads, so little polystyrene particles, for example, with a mobilized DNA on the surface, and they're put together with the cells into the droplets. So that's depicted here. So this is the entire workflow of this method. So you make droplets with those barcode beads and with cells together. And then, yeah, you have the microparticle and the cell together in the same bead. And then you lyse the cells very fast. So already in the encapsulation, you put in some lysis agent, the cell wall breaks, and then all the transcripts, all the mRNA can bind to the DNA that's on the surface of these little microparticles, on these barcode beads. And then you do a reverse transcription. So the mRNA is translated back into DNA, and you get a double strand on your bead. So you have captured then as DNA all the mRNAs that were coming from this one single cell. And then you can break the emulsion, then you don't have droplets anymore. But you just have the beads where all these DNA strands are attached to it. And then you actually rip them off the beads basically, and you sequence them together. And because of the barcodes that were attached to these little beads, you can later on tell which transcripts come from which cell. So that's depicted here. So this is what you would get out of the DNA sequencing run, for example. You would get a lot of different cell barcodes. Then you have something called a UMI, a unique molecular identifier. So this is a random sequence in each barcode. This is completely unique for each molecule, so that when they're amplified for sequencing, that you can then tell how many times you're seeing the same molecule. And then you have the cDNA. So this is basically the gene that was produced, that was read off, transcribed in the cell. And so then on the computer, you can sort of cluster them by cell barcode, which of these reads come from the same droplet. And then you look at the unique molecular identifiers for each gene to see, okay, this gene, I'm seeing it 3 times because I have 3 times the same unique molecular identifier. So that's really just one molecule. And then you can make a matrix. So this is basically seen here on the right in gray. So you can see all the genes that are differentially expressed in the different cells. And here you have the different cells in your sample. And you can see in this diagram, for example, that we do get very different expression pattern in different cells. So here in A and B, they have mapped this. So this is some tissue from an eye, and then you get these different cell types. And indeed, the different measurements from single cells, they all cluster into these different clusters, showing you that it's a different activity, a different gene regulation, and indeed a different cell. And yeah, okay, I actually took out the different slide, but so this is drop-seq. They just use these polystyrene beads with immobilized DNA. But in drop, or this commercial variant of it, this 10x genomics, they use little microgels to bind the DNA on the surface, and they're little technical advantages to this, but the general principle is the same. Okay, so this is just one paper that's very recent, that's an application of this. So for example, here there has been a big consortium, a lot of different scientific groups working together to map all the different cell types of the mouse. So now we basically know, we have a benchmark data set where we know what cells in the body of a mouse have what kind of gene regulation behavior. So what genes are actually produced and expressed in these different tissues. And usually, so there were a number of high-profile publications over the last years since this method came out, where people found a lot of new cell types. So you think that, I don't know, there are only 3 different cells in the kidney or whatever. I'm making this up. I don't know how many there are in the kidney. But then they found that there are actually a number of additional cell types that were unknown previously, and there are only a few cells there, but they may also be important. Okay, so this is for eukaryotic cells. And now I'm moving to prokaryotic cells. So again, so this is bacteria. And again, there we want to measure the genome itself, not the transcriptome. The transcriptome in bacteria is also interesting, but it's actually very challenging to measure because there are only very few molecules and the cells are much smaller. But they're already different in their genome. So the human microbiome, you might not be as familiar. So this is also my research. So I'm giving this little motivation pitch why this is an interesting thing to work on. So the microbiome is of course everywhere. So there is a microbiome in the ocean, the rivers, the soil, and it's all also very important. But in the human microbiome alone, the bacteria that live on our body, they're also very important. And this is what I've been working on in the last years or right now with my current projects. And actually more than half of the cells in our body are not human cells, but they're bacteria. So there are a lot of cells living in our body, and they're actually sort of part of our biological functionality. And 99% of the genes in a human are bacterial genes. So because all our human cells have the same DNA, but the bacteria are different, they have a lot of biochemical potential. So they can make a lot of things, convert a lot of things. And together they're a lot more powerful biochemically speaking than the human cells. And with the gut microbiome alone, there are more than 100 disease associations. So there are a lot of health and disease states and even mental illnesses. So that's displayed here on the right. There are all kinds of things that are known to be influenced by the kind of bacteria that you have in your human gut. But bacteria are also relevant in other organs, not just the gut, but the mouth, the nose, the skin, the vagina, the lung, everywhere. Okay, so now that we have this large diversity of bacteria, and I mean, I don't even know how to pronounce this number, 10 to the 13. I mean, this is a very, very large number. So you have a lot of different bacteria everywhere. And how do you look at those genomes? So the classic method that's not actually depicted here is metagenomics. So you need to have very high throughput to study this. So the classic way would be to just sequence all the DNA in your sample. You just take your sample, whatever it is, and then you extract all the DNA and you just sequence it. But then you get a lot of different fragments and you don't necessarily know what belongs together. So in order to see what's there, you usually sort the mess that you have against some reference databases. So against the known and cultivated bacteria. But they're only a small fraction of all the bacteria that exist. So we want to also be able to look at the genomes of uncultivated, unknown bacteria. So for this, we really need to sequence the genomes of the individual single cells. And so this method that has been developed by a Japanese group here that does this very well is that you encapsulate those bacteria again in little droplets. And in this case, you also add a specialty low melting agarose, so that these droplets actually gel. So first you encapsulate the cell and then you cool it down and you get a little microgel. And once you have this gel, you can take the oil away and you still have the cell trapped in the gel. So you see this down here in B. And in the first picture, you just see the droplets in oil. And then you remove the oil, you have less of an optical contrast, but you see that these gels are still intact. And then you can lyse the cell. So you remove the cell wall and everything, but the DNA is trapped into gel and stays there. So then you just have a gel with DNA inside. And then you can amplify this DNA. And this is what you always have to do to obtain single cell genomes. You need a lot more DNA. So they're often referred to as SAGs, so single cell amplified genomes. So this, you get this with low contamination and very parallel in each of these little microgels. And here they put a DNA dye, so you can see that you have a lot of DNA trapped in each of these little gel beads. And what you can then do is that you individualize, you separate all these living beads in separate well plate wells. And then you can basically get rid of the gel by heating it up, and you can add barcodes and other sequencing agents, and you can sequence the thing. And so this is some of my own little pictures, microfluidic, to actually generate these microgels. I'm letting this run. So microgels are a little bit more difficult to make, and it's a bit slower, so you can parallelize it by splitting the droplets and go back here. So then you can make many in parallel, but you can also add these little wiggle lines to your chip design to mix the content of the droplet and so on. So you can do all this on the chip. And this is just one data set here. So this is a bit technical, but one measure that's quite important is how complete is the genome. So it's very challenging to get a complete genome from a single cell. So normally when people do this, the quality is very low. So you get fractions of that cell, and you know that it belongs to one cell that's already valuable, but you don't get the entire genome. So here they have the completeness score and the number of single genomes that they have sequenced. So you can see that most of them are actually not so high in quality, but you do get a number of high quality genomes also here on the left side. And then here sort of shaded a bit in blue at the very left, these are pooled genomes. So then when you see that several of these fragments actually belong to the same kind of bacterium, you can then pool those fragments computationally, and you create one genome out of those that has a higher quality. And that way they were able to assemble a number of very high quality genomes out of just a few cells. So that works really nicely. And then they can do analysis. So in this particular paper where this data comes from, they worked with a lot of mice, and they had the same mice that were first had a normal mouse diet, and then they fed them on a diet that was very high in fibers, insulin fibers, which is supposed to be very healthy. It's supposed to be like a probiotic, something that stimulates good bacteria. And then what they could see afterwards in their genomes is that, so the kind of bacteria that were then in the mouse gut changed. So they were different bacteria. And after they have these genomes, they could then analyze the gene clusters in those bacteria and see which genes were present that can actually utilize these fibers and make other biochemical products out of them. Okay, so this is just an introduction what you can do with this. And now, so I'm not entirely sure how we're doing in time, but I have almost done. I'll just give you a very brief introduction about what I use this technology for in my research. So I'm looking at interactions. So because so bacteria don't really exist individually in nature. So in the lab, we often use single cell cultures, so clonal cultures even, but in the environment, they always come with other bacteria together. And a lot of the functions that they do, biochemical functions and so on, they are dependent on these other bacteria. They don't actually do these functions on their own. And also, this is often growth related. So most of these bacteria do not grow in the lab. And one of those reasons is also that they need other bacteria to really to complement their metabolism. So this here is actually a single plug of bacteria from a tooth. So these are the different bacteria that grow together in a little lump of biofilm, if you want. And they were stained with DNA sequence-specific stain, this so-called fish probes. And so you can see the different kind of bacteria in different colors, and you can see that they arrange in particular repeated groups, so different bacteria appear together. But we know very little about this, so we need to understand more, and for this we need very high throughput experiments. And so droplets are very good to do this. So the current most high throughput technology for single cells is actually the flow cytometer. So you basically just flow single cells. It's also in a way a microfluidic chip in there if you want, where you just flow cells in a channel, and you also even generate droplets, but just in air, and they shoot past a laser, and then you can read the fluorescence signal. And so most of the classic single cells do just that. You take your cells, and then with these machines, you can sort them into individual wells. But if you want to do things like transcriptomics or single cell genomics, then this is very challenging to do in these plates. You need thousands of these well plates, and you get a lot of contamination, and it's extremely expensive. So this is why these previous methods that I presented are a big advance. But you cannot do with this technology interactions, because you don't know what this bacterium does in relationship to the other ones that are also sent through the machine. But in droplets, you can have more than one cell together, and then you can study what this particular pair actually does with each other. So and this doesn't really exist yet. There are not a lot of useful tools for studying interactions in droplets. There's some methods that could be used, but that haven't been used, and they have to be adapted and so on. So I'm developing these methods. And in particular, with the Fond de Citonisation grant that I just got and that will start soon, I'm looking at the bacteria in the human nose, and I'll co-encapsulate them into droplet and study the interactions with the goal to fight certain pathogens that often live in our nose and that can cause problems when we're in hospital, for example, and the immune system is down. These bacteria can cause infections, and a lot of people die from this. And they have been with you all along, and basically the infection doesn't come from the hospital, but you bring it with you into the hospital. So it would be nice to be able to get rid of these bacteria. And so, yeah, for this, I'm actually also looking for people that are interested in working in my lab as student assistants or PhD students, and there are going to be positions available for molecular biology work in this context, but also for technology development and automation. So I'm doing a lot of open hardware as well. And yeah, you can just talk to me about that later. Thank you very much.
Thanks a lot, Dr. Iaz. An amazing presentation. So now someone has questions. I see a hands up of Gonzalo.
Thanks, Toya, for your presentation. Really cool. I like a lot this idea of single cell analysis. And now that we can separate cells in different droplets, I think maybe this is kind of the mix between population study, that could be the cytometer, and dynamic study, that could be like study fluorescence of that single cell on time. And in our lab, we are very keen about dynamics. So that kind of technology are really cool, and I'm waiting to see how you implement that. So in that sense, how is this work? Has a lot of advances recently, because the papers that you show are really recent. So I think it's a extensive field and very competitive, I think, because it's constantly developing new things. And also I want to see if you in one workflow, you have at the end a plate reader, which is a nice thing in common with our methods. So how do you use those plate readers to measure single cell data or signals?
Right, I'm glad that you're interested in it. I guess there were different aspects to your question or your statements, but first with the plate reader. So there are ways to use plate readers to do, for example, parallel qPCR measurements to look at the abundance of different genes in different cells. But when I showed the plates, then this wasn't really used for fluorescence readouts. So in these experiments, the plates are usually just used in the end to individualize the cells. So they're already individualized in droplets. But for example, in those single cell genomics, you use the droplets only to amplify the genome randomly so that you have a lot of fragments of the genome, but then you still have to prepare them for sequencing. So you put them into individual wells with, for example, barcodes, so that when you sequence all those different cells together, that you know which cell was sort of one cell. So putting in the first method, in the single cell transcriptomics, you put the barcode into the droplet also. It's possible, but it's effortful and potentially expensive. So it's easier to do it in well plates. A lot of these chemicals or these protocols have been developed for well plates in the first place. So that's a bit easier to do. And especially because you can, in these flow cytometers, you can already look at the amount of DNA that's there. So you can see for which of my cells did I manage to amplify a lot of DNA. And then you just take those successful beads in a way, and you put them into wells for the chemical processing, if you want, for the molecular biology processing. But you don't need a fluorescence readout like in a plate reader for this particular step. But there are alternative methods that do use the plate reader, like this qPCR approaches. That's definitely possible. Measuring signals over time is a bit tricky. So it's all possible in droplets and people do it. But I think mostly groups that use this, they use, for example, droplet traps. So you generate a lot of droplets. And then instead of having a well plate, you have a microfluidic chip with little traps. And you can have many thousand or even tens of thousands of little droplets that you can see on the chip at one time. And you can put this under your microscope and you can monitor them and screen them over time and go back to the same droplet. But then it's very difficult to get them out again, a particular droplet at a particular point of time. So then you use just microscopy. So I'm not really doing this so far. So I use sort of microscope setups for droplet sorting, for example, but not to monitor them over time. And so it's just a question of how high your throughput is. So if you want to do millions of experiments in parallel, it's very difficult to monitor them and then use them further to process them or get the cells out or so. So instead, there's sort of no microscopy, so you can't really follow an individual droplet, but they're just in one huge pool. And in the end, you see what you had in sequencing, for example, but you don't really have a time series. So it's possible to do these things, but it's difficult to do all of these things at the same time in the same experiment. Do you see what I mean?
Yeah, thanks. Also, I want to mention that we have a lot of makers here, so you're welcome. A new maker in the community, and hope that some cool projects arise from this interaction and make some open scientific hardware between us.
Absolutely, I'm very excited about that as well in the Institute. It's a main approach for me. I built most of the equipment, well, myself, meaning I do something, but then a lot of people in my sort of team or collaborators do something as well. So we build these together, and this is one of the things I really like also about the Institute, that there are students, but also other professors that follow this approach. It's not mainstream at all. I think it has a lot of advantages, but there are a lot of people that don't get it. But I'm glad to see that you're also enthusiastic.
Thanks.
So we have Rocío Artigas. Has a question?
Yeah, thank you. I have a question. I didn't remember if you mentioned, but what kind of cell would be useful for the mouse experiments, or what level of differentiation will be needed in the mouse experiments you showed in previous slides?
Right. So I'm going to share my screen again. So if I, oops, share screen has stopped. Sorry, I'm going to do it again. Here. Yeah, do you see my slides again now? Not in presentation mode, so I can show you the slides that I'm skipping.
Yes, we can see it.
Good, thanks. Should be here somewhere. Yeah, so this is, for example, this other method that I like even better, and I'm developing a barcoding approach at the moment, and that's based on this method. So the one that I showed earlier here, this drop-seq method, basically, that uses these little microparticles to have DNA strands attached to it. But and the other method is called in-drop, and it's this one. So this was the other one that was sort of published back to back in Cell. And they use these little hydrogels instead as barcode beads and attach DNA to those. And the cells that they used in their initial study, so there are now many single cell studies papers out there, but their initial biological target was indeed stem cells. So here they've looked at different stem cells, and then you can tell when they're still in the pluripotent state or if they have differentiated into different cell types. You can see that on the description, on the transcription profile that they have. This little box here on the right. It's just a clustering algorithm applied to the data sets. Does that answer your question a little bit, or did you want to ask some?
And for example, I'm looking at that now. For example, in the slide 13.
Mm-hmm. Yep.
For this experiment, what would you need in terms of differentiation of kind of cell?
So I think that I'm not very familiar with this particular study, but I think it's a big consortium, and I think they had different people studying different organs with the same protocol. But they just take they basically dissect the mouse, they take the whole organ out, for example, and they just completely dissociate it so that you have all the individual cells. So I think there's no further selection applied to this. They have all the cells that are in the tissue just go into the experiment.
Okay.
So you can do this with any kind of cell, just not with bacteria. So there are actually a number of reasons why this doesn't work with bacteria. So first of all, the most important is that the transcripts of eukaryotic cells have this poly A or poly T. I'm confused now because you have to put the complement of that to the DNA barcode. So this is probably here in the picture I'm getting. So, okay, so you have the poly T on the barcode. So the poly A is at the end of the transcript. So you have this long repeat sequence at the end. And this is what they use in these methods to capture the mRNA specifically. Bacteria don't have this. So their gene transcripts are just the transcript itself, and every transcript is different. So it's very difficult. You can do a targeted approach, but if you want to have all the transcripts from one cell, it's hard. But it's also more difficult to break the cells open and so on. But with eukaryotic cells, there's really no limit which kind of cells you can use.
Okay, thank you.
Thanks.
So if there's no other question, thanks a lot, Tobias, with your amazing presentation. And now I would like to introduce Daniel Friedman. Daniel. So thanks a lot for being here. He's a postdoctoral student of the UC Davis in California. Yes, and he will present us a poster about titled Active Inference for Communicating Systems.
Does it look okay? You can see my slides? Great, thank you. Hi, everyone. Thanks. And just to clarify, I have 3 minutes or how long?
Yeah, you can pass. You have more minutes if you want to.
Okay, I'll go for 3 plus a little bit for Q&A. So, hi everyone. Thanks so much for having me here. This talk is called Active Inference for Communicating Systems. I'm Daniel Friedman, and I'm a postdoctoral researcher at the University of California in Davis. So it's in Northern California. And I'm presenting on behalf of TeamCom, which is some colleagues who I work with on these topics, and I'll talk about us at the end. And congratulations on your first networking event. It's a cool topic and good ideas. So there's a lot of facets to active inference, and I'm sure if you ask 100 people, you'll get 100 answers. But I just want to start off by drawing out 3 of the main threads. The first thread is the free energy principle, or the variational principle, and that specifically draws on the fields of physics and statistical mechanics. And the work there has been primarily by a professor named Carl Friston in the UK. And what it does is it draws upon a few different areas of physics related to far from equilibrium systems and sensing systems. And it loops it together in this way that ties together internal and external states. So here reflected by the brain and its surroundings. And it basically separates them down the middle with what's called a Markov blanket that reflects conditional independencies about these internal and external states. And the Markov blanket is pierced on the way in by sensory states and on the way out by action states. And as the image might imply, but that was just the quick version, as you could have probably imagined. And as the picture implies, this is also a framework that draws a lot on biology, specifically neuroscience, which is Carl Friston's background, but also areas like evolution and ecology and behavior. And explicitly thinking about internal and external states for organisms and multi-scale systems allows us to take a lot of interesting threads, not just from the, say, reductionist biosciences, but also a lot of approaches related to systems and complexity adaptive systems, complex adaptive systems, complexity science. This also draws on the work of autopoiesis, on semiosis, on meaning generating systems, on self-evidencing systems, and a lot of other work on cybernetics and control theory. So all these threads kind of come together, everything from statistics and mechanics on the left side here to biology in the middle to holism and other types of approaches related to systems on the right. And just to convey a few of the ways that people are applying this topic of active inference in recent analyses, on the left is an example of a robot swarm. And so this is the case of communicating agents here that could be ground-based or air-based drones or different types of vehicles. It's cool that you have an engineering focus here. And it talks about how this systemic way of thinking about action and perception could apply really well to these kinds of definable systems, and potentially things like digital twins could be used to implement a simulation of a system or understand what kinds of control mechanisms each drone should implement for a given strategy to be realized. A second area where active inference is being used is in the area of mental health. And this is from a paper recently called Recent Advances in the Application of Predictive Coding and Active Inference Models Within Clinical Neuroscience. So there's a lot of interesting ways here at the psychological, but also at the cellular level, that there's ways we can reconceptualize of diagnosis or of the treatment of different kinds of states. And the image reflects this multi-scale perspective from the synapse and all of the neurobiology at that level on the bottom, but also progressively higher and higher levels reflected by whole brain analyses, as well as by an understanding of the social dynamics of an individual. And then the last use case that I'll bring up is this topic of online teams and remote work. This is actually one of the papers that TeamCom has written. So it's our colleague Alex Viatkin and several other members of the TeamCom that we published recently. And here we conceptualized of the individual humans on a team as being these technologically embedded and active agents that are able to basically get sensory data from servers, whether it's video or text or updates for software, and then they push actions. And that could be things that are passively collected like a video, or it could be actions like typing. So in this way, we might be able to design the dynamics through the communication channels of real online teams that are able to reach the goals that we want to have for our teams. For example, being productive or inclusive or accessible, all these different things are really important. And so I'll just close by saying, if you're interested in learning more, we have a weekly podcast where we discuss papers. We actually did it this morning. And on Twitter, we post about that. We just announced what dates and what papers we'll be reading for the next 2 months. So if it sounds interesting, then come learn more, because there's a lot we could talk about it. So maybe in whatever time is left, we can have any questions. Thanks a lot for listening.
Great. Thanks a lot, Daniel. So now it's open to questions. So Gonzalo, go ahead.
Yeah, first I want to know how you get known with autopoiesis and the relation with cybernetics.
How did I come to learn about that connection?
Yeah.
Couldn't say I remember the exact moment, but I've always been interested in systems theories and in approaches to action and multi-scale systems. And so in that sort of nexus of ideas, there's so many historical threads. So for example, control theory and cybernetics have very different developments between the English-speaking world and the Russian-speaking world. So some of the Team Com members are in Russia. And so there's just quite a divide. There's a lot of untranslated work. But I would say that there's also another divide with other languages, like with Spanish-speaking literature. But I think that autopoiesis has broken through in terms of being like a word that people can kind of understand, that links together some of those more meaning generative components of these reflexive control systems. And then there's like the engineering, like, is it going to be the capitalist engineering or the communist engineering angle that gets quantified? And that has led to some powerful simulation approaches and analysis approaches. And then there's this other side that I see as being more about meaning and understanding. And now today, we're trying to build on the strengths of all these different traditions and come to something that is both tractable and helps us model real systems and drone swarms and delivery networks and things like that, but also might capture some of these more experiential or phenomenological aspects of hierarchical systems.
My second question is about your work with online teams. What's the goal of this? I kind of understand something similar to like a GitHub workflow where people interact with a database, but I don't get the goal of that research.
Sure. So the first is just the general realization that increasingly teamwork and communication is being mediated through digital technologies. Case in point, right? And that includes various levels of augmentation, like a live translation or just a deepfake agent or internet lag. There's new affordances and there's new challenges, constraints in the technological communication space. So at the most general level, we're just trying to understand like, whoa, all the theory of behavior used to be about in-person interactions. Now that's being transformed because the sensory and the action affordances are very different. That's also drawing, so that's qualitative insight drawing from an activism. But what these kinds of tools that we lay out would be important for, ontologies, narrative, formal documents and tools, or the ONFT that are proposed, it would relate to the design and control of systems that are mediated by these kinds of communication dynamics. And so we could reframe a lot of these sort of loose questions about how communication happens. That's pretty broad, but I think we go into a few different examples, and you can definitely think of several examples from the integrated hardware and the software perspective and the narrative level. How are we going to make participation happen? Well, it turns out everyone needs internet, but they also need to have the attentional regime on the question, and they also need to be aligned with the narrative. And so how do you get that full stack understanding? And then how could you implement that in a real system and say, okay, well, the rate limiting step here is these 200 people need a hotspot internet versus hey, the rate limiting step in this system is actually, we need these 200 people to get together and have a shared narrative. They all have high-speed internet. They're just not working for a different reason. And so instead of just going around fishing randomly, we could actually formalize that and potentially make better interventions.
Great, thanks.
So Rocio has another question.
Yeah, I would like to ask if you can tell us more about the mental health approach.
Sure, thanks for the question. Carl Friston's training was in neuropsychiatry. And so he has done a lot of foundational work in applying the neuroscience, modeling, angle, fMRI, all these methods. And then through the development of the active inference framework, it has turned to mental health in sort of a new way. So the most basic level is some of these methods are used in studies of fMRI or in EEG to analyze just biobehavioral differences between groups. That's just the first pass answer. Here's the deeper, I think, account of mental health in the active inference framework. Fundamentally, it states what we're doing not as reward maximization, but as precision optimization or uncertainty reduction. Precision maximization, uncertainty reduction, similar. And so a condition or a state such as depression isn't a deficit of reward finding. It's actually a maladaptive space, maladaptive point in the behavioral space that makes the organism in its niche pursue fulfilling beliefs, such as I'm in bed, I'm depressed, I'm not going to do anything. Well, you're right if you stay in bed. And so it's not about the getting reward up in a certain way, leading to dopamine being understood as a reward molecule. Actually, active inference frames the brain regions, the molecules, the behaviors, the manifestation of these complex socially enacted phenotypes. It phrases it in a totally different way. And that allows us to be like, all right, if it is about precision, then what are the tools that we have at our availability now? So that could range from different kinds of interventions in the system, from the molecular to the cognitive behavioral to the niche modification that would reflect how we diagnose and categorize different kinds of cognitive diversity or differences in experience, as well as the kinds of things that we would do to intervene. Understanding that at the circuit level up to the niche and the social level, it's about that precision optimization from a generative model, and people are just anxious when things are uncertain, and they feel not good when they can't resolve that uncertainty productively. And so those are things that are quite naturally accommodated by this kind of information foraging or multi-level generative model approach. And they don't really fit into this reward optimization approach, because when we're scrolling through social media, it's not reward we're pursuing in that case. And in many other cases, it's pretty clear to see that it's actually precision, and that's multi-level from the visual to the narrative. So that is something that's going to help, I think, contextualize a lot of different states that people are having.
Okay. Thank you.
Okay, so I have a question. Thanks how you pose the active inference framework in neuropsychology or cognitive science. And how you move that framework of the embedding a generative model of the brain to the social, the third column that you explained to us.
Thanks for the question. So it was about like how we move this sort of understanding of systems having this certain approach, potentially with certain mathematics on board. How do we actually implement that in the online team's case? Is that the question? Okay, so I think that there's two elements. There's the exoteric, the ones that are consumable, and that would be really the tools that people use that shape their everyday digital life. So people don't need to understand neural networks to know that the recommendation engine of a website is a neural network. And so, for example, an online learning site, instead of doing a machine learning model that optimizes dwell time or some sort of surveillance capitalist exploit, you could have this generative model reflecting the student's uncertainty. So in that sense, the tools could be purely on the back end, and people wouldn't need to have any other understanding of what was happening other than knowing that their informational foraging was being shaped in a way that it's already being shaped, just in a different way. So the first way that it could be deployed would be in tools that would be truly invisible for people, but would present themselves as like better recommendation or attention management tools, as well as communication interfaces. And then to be short about the deeper way, if people understood like, hey, you know, there's things that the brain knows that the neurons don't know. So there's going to be things that my small team or my community is going to be able to do that I'm just not going to be able to do or know about. Even if I think I know what's happening, it's just going to be a totally different level of analysis. How do we design those kinds of systems that actually take advantage of people's preferences and strengths and all these things, and gets that higher level outcome to be engineered? And it would probably have something to do with how people understand their role in the system. And so that would be a more psychological understanding of work, which hasn't quite been deployed in such a way, especially for remote teams, because that's a new affordance from an evolutionary point of view.
Okay, thanks. Thanks, Daniel. If there is no other question.
Thanks again for the invitation. And I really look forward to hearing more of these talks and discussion.
Yeah, thanks, Daniel. So now I would like to present to you Carlos Valles. He's a PhD student of the IIBM Católica. He works in the lab of brain-machine interfaces and neuromodulation, and the title of his posters is Brain-Computer Interfaces for Decoding Covered Speech with Limited Data.
Thank you, Gabriela. Okay. Can you see the presentation?
Yes.
Yes.
Okay, thank you. So I will start explaining what are BCIs and why we need it for communication. So BCIs are brain-computer interfaces that allow us to communicate our brain to perform an action through a computer. So in this case, I would like to focus my thesis project on BCIs for restoration of communication. So the basic principle is that you put a recording system that measures your neural activity. It can be on the scalp, on the cortex, or even with MEG based recordings. And the idea is just to capture the electrical activity and then to interpret this electrical activity to form some text or phrases. So as you can see here, the idea behind this is that you put the person reading or listening to an audio recording, and then you have the labels between the neural activity and the text. And with this, you can decode a speech from the brain. The idea of this is to, as I said before, to restore communication for the treatment of aphasia patients, patients who cannot talk, like ALS patients or lock-in syndrome patients. And also this kind of technology, if it progress further, can be used for industry applications and things like that. So the idea of sorry. The current status of brain BCI for communication is that it has been shown possible to decode text or phonemes from the brain. And actually, in the paper of Herf in 2015, he was able to decode whole phrases directly from the brain. The problem with this technology, or the thing that have not been explored, is that the working mechanism and dynamics have not been fully explored. mainly because the language and neurolinguistics theories behind this, behind the internal working, are also not fully understand. So we know that it works, but we just don't know how it works, or what features or what variables could be beneficial for the decoding of these signals. So just to be clear, there are two main kind of experiments. The experiments that decode cover speech, that is similar to imagine speech, and the other study is the decoding of perception speech. Is when you listen to some speech or you read some text. So the idea behind this is that I want to progress in the decoding of cover speech, but the problem with cover speech is that is the naturality of it, because if you are doing cover speech, you are not producing anything. So in terms of labeling, it's very difficult, because you have to be looking at a screen and the researcher or the experimenter doesn't know what are you saying. So you have a really big problem collecting data. So the main problem with cover speech is that you don't have enough data. And when you have data, this data is very small. So you have to collect a large range of subjects in order to get raw results. But what if we have already a big data set of person doing a similar task? So sorry, I forgot to put the, so if we have a really big data set, we could use this data set, which is similar, which in this case is a speech perception. Maybe we will do the link for speech production, which is cover speech, to try to make a link between these two modalities, which are different in naturality, but can be more or less linked. So with the use of regular neural networks, I plan for my PhD to try to understand and create better models for the decoding of cover speech in the scenario with limited data. So sorry, I forgot to put the reference here. But the data that I'm using is from subjects there, but this is a perception task. So you are only listening to what an audio recording, So it's not the same as a cover speech tag. So how we use this really big data set to try to modify it to use it for cover speech? That's the question. And to answer this question, we first need to understand how the dynamics or the relations between perception and production. So first, I was trying to train a model to decode perception speech from this dataset. And as you can see here, the results are not conclusive. So I am obtaining exploiting gradients with this method, which for what I read is more or less common with recurrent neural network. So this is something that I have to fix for now. So at future work, I need to look and understand why there is exploding gradients. And also, I could try to do gradient clipping to solve this issue. But we need to, I think it's really good to to ask what is the difference that this data set provides that even with with smaller data set, you don't get these kind of results. So I think I need to try different things and different modalities to do this decoding. But the problem is that it's not really clear what are the modalities or what are the main variables. So for the future, I need to try to look and understand which are the more important variables, but try to beat them with a certain criteria in order to don't get lost in infinite variables. So that's the presentation. Thank you.
Thanks a lot, Carlos. So now it's time for questions. So Gonzalo, go ahead.
Thanks, Carlos, for your presentation. As an AI enthusiast, I like it a lot. The sequence-to-sequence models here in recurrent network. So one thing that I want to point is the kind of recent development of transformers in sequence-to-sequence models that can help you in this task. So there's a lot of advances in AI that can be used now, and with the power that show GPT-3 in sequence-to-sequence tasks, I think maybe transformer could be a nice way to, or a nice implementation of a recurrent neural network to use in this problem. I like it a lot, and brain-computer interfaces are exciting. I also think that generally biology-computer interfaces are cool. I also, in some part of my work, I want to do bacteria-computer interfaces, doing maybe a feedback between optogenetics and luminescence emitted by bacteria. That could be really nice. So I think we have a lot of common and things that we can work together.
Thank you.
So more questions? Okay, so if there is no other question, it's time now to present myself. So
maybe I can present you, Gabriela.
Okay. Thanks.
Okay, so Gabriela is also part of the laboratory of brain-machine interface and neuromodulation. She's a PhD student of the biomedical and engineering PhD, and her topic of interest is self-regulation and active inference, which is the name of his presentation.
Thanks a lot. So can you see it? The presentation with the whole screen? Okay. Okay. So one of the main topics of my work is self-regulation. That is the learning to control where we have experienced a neurofeedback, when we have a neurofeedback experiment. So as Carlos said, neurofeedback is based of signal processing and detection of a particular neural substrate that could be a particular node of a whole brain, a network, or a neural link some particular numbers of neurons that are in a closed loop feedback to the subject as a visual information, haptic or auditory stimuli. And that is through brain-computer interfaces. This setup has been shown to result in both changes in brain activity and in behavioral modifications. So one of the main goals of this setup is to have a clinical impact in a very broad fields as neuropsychiatric disorders or post-stroke rehabilitation, Parkinson's disease, etc. But the main thing is that the optimal experimental setup or neurofeedback paradigm currently present a learning rate less than the 50%. So that's very bad. And the mechanisms that are underpinned of these self-regulation mechanisms are poorly understood. There are some insights that are very related with the main findings that we have for the moment, that is related with what is at the moment understand as the striatum and dopamine system. And how we go deep into that is at first we use an experiment and data acquisition from a real-time fMRI that from a total 18 subjects were divided in 4 groups where they test 4 different factors in terms of how the experiment is delivered. So one of those just gave them the feedback of a particular area. In this case, is the supplementary motor area. That is an area related with sensorio-motor integration and coordination. Another group with instructed motor imaginary, that is like to imagine or replay something related with movement. Another with a proportional monetary reward at each moment that the upregulation activity of that target area is increased, and another group with these 3 factors. So from the previous experiment, we took the functional connectivity analysis, and we go a step further and ask what are those networks with more evidence in the self-regulation in subjects where learn and who don't learn. And for that, we use dynamic causal modeling. That is one of the methods known for fMRI to test effective connectivity. And we choose particularly the Bayesian model comparison by family inference methods that divide subsets of models to compare. This is because the main difficulty of this kind of experiments is the little amount of data in a subject and in the whole set of subjects. So the main areas that are identified from functional connectivity analysis were the striatum, the anterior cingulate cortex, the supplementary motor area, and the frontal area. And how this is modeled in the DCM is that each area is modeled as a neural mass model. So from the hemodynamic information, we can infer the neurodynamic information, and we build the different connectivity, the different connections between the different nodes. Then we have to define where is the input to that node, and then we have to define which is the modulatory input between the nodes or in the edges. And that is understand or interpret the neurobiological interpretation of that will be which is the impact of the experiment in that network. So some preliminary results that we have. As I said, we have to divide different subsets of models to compare. And the model with more evidence were related with almost a fully connected edges, fully connected network between these frontal SMA anterior cingulate cortex and striatum node with the input to the frontal node. And with the family comparison, we could define which were our best three models. That is evidence in this Bayesian model selection histogram. But what we wanted to see is where okay, so we have the best three models, and we can see through the whole experiment that were 8 rounds, and in the 18 participants, that is not one particular model present or with more evidence in the experiment. So we can see like maybe the subject will be switching between different models. Another thing that we wanted to test, it was in those participants that we defined that they achieve a learning in the self-regulation experiment, that were able to self-regulate, which was the parameter in terms of modulation of the networks. And we can see that it is from the striatum to the anterior cingulate cortex, the parameters that have more evidence. So, how this is related with active inference? First, the conclusion is that, okay, so we see that the striatum, and we know that the striatum is a particular hub or node of dopamine activity and dopamine projections. And the history of the striatum is related with reinforcement learning. That's the inspiration of the reinforcement learning equations. But as I said, it's not one particular node or one particular network that is presented in the current experiment. So maybe it's not only like the simple interpretation of model-based or model-free learning that we have in reinforcement learning, but it could be more orientated to these other corticostriatal loops from this hierarchical system, when the dopamine is not only the reward system, but also is, as Daniel was said a little bit earlier about the precisions belief about different sets of policies that will be selecting in the process of learning. As future work, now in this framework, there has been some simulations that relate brain activity and brain learning under the active inference and free energy, variational free energy minimizations to emulate brain and behavioral learning or activity. So one of my goals is to design an agent based on active inference and free energy minimization using this hierarchical predictive coding that were able to simulate a neurofeedback experiment. So this is like the more naive agent simulation that I can do, but it's a first step where I set to this agent to be in a neurofeedback experiment. And the goal of this agent at this moment is to be in this upper position, like the up regulation of the self activity. And we can see that it is able to infer and in which position is this agent and learn to be in the upper positions. Another thing that we want to do is also to work with a better fMRI data to validate this model in terms to the functional and effective connectivity. So that's my presentation. Thank you for listening.
Okay, I will kickstart the questions. Nice work, Gabriela, with the simulations. And I see a lot of active inference, but I think that how the active inference is related to the policy. I don't understand that part. I understand policies based on reinforcement learning,
Yeah.
but I don't know this new approach. Can you explain it better to me?
Okay, so exactly at the first time, since we have this parallel of reinforcement learning and the reward system, the policy sets the actions of the actions that we have to choose in order to change from different states. Yeah, that's the main understanding of reinforcement learning. Okay. So the thing is in active inference, maybe Daniel could explain better, but the difference is the way that is optimized, the action, the perception is both embedded in the minimization of the free energy variable. Because in the other system, you have the division between what is perceived or observed and what is act. And what it is done in the code or in the framework of active inference is that are both minimized. So in fact, sometimes it's a problem. But
Okay,
maybe Daniel.
So it's like a multi-objective optimization problem, and this both the action and the perception are merged together. There's not just action reward, so it's you minimize the energy in the process to feel something and do something about that. That's the okay. Thanks.
Maybe I'll add on a little there, then ask my question. So there's one sense in which a quantity called free energy is what is being used to guide this optimization across multiple scales. And that's actually a common terminology even in the machine learning community. So you'll find like variational inference and variational Bayes being used in multiple kinds of models. You could do it for multiple regression. Okay, so part one is free energy minimization as a guiding heuristic for multi-scale models. And then really the second piece is where there's a homology between the model-based and model-free, just as Gabriela brought up, but then like a little bit extra, which is something that's actually in a few other papers we won't go into here. But fundamentally what it has to do is in the model-based, the organism's getting rewarded when there is basically a confirmation of the model. And this is kind of similar, except that the stimuli that the organism is seeking precision on, not reward, are those that are optimally informative given a deep generative prior of the sensory observations that are received. And so in that way, it allows for a lot of nice things like counterfactual reasoning or implementation of the mapping, learned mapping from the sensory states to action policies, rather than sensory states to sort of neutral representations. And then from there, doing this inference problem or assigning a reward value to different states, like in Q-learning. This is like a direct mapping. So action states are still different than sensory states, but the way that they're mapped has a little bit of a different connector and certainly different mathematics than in other more classical cybernetics approaches.
Thanks.
Yeah. My question, Gabriela, for you was like, you mentioned the biological tractability of different kinds of models. So what systems were you thinking about, or what do we look at in a system to evaluate whether a certain modeling approach that we take is tractable for that system to actually do?
So here we have, well, the reproduction here in the behavior. The thing is, here the behavior is inside the own, like the brain activity. That could be the own agent model. So that's the main problem that we are having here, how to solve. As you were saying, like the general framework is the Markov blanket, like you have the external and the internal like environment division, and there you can have the action. But in our case, the action, as we were thinking, is inside. So one way to solve it is, as I, this is a work in progress, so I don't have the solution. But since you have the precision of a model, of a set of models, and you can simulate that as a neurophysiological patterns of activity of dopamine, maybe from that we could interpret some like internal validation. But it is under debate.
No, it's an interesting question, because a lot of times, like from the ecological psychology side, it's thinking about the ecological embeddedness of a forager or something that's moving. But you're studying something that is a little bit reflexive, because it asks, what can we know about ourselves through this kind of control mechanism, given that it's probably an unlikely affordance from an evolutionary point of view, especially.
Yeah, I mean, another main area to criticize is that, okay, so we have these policies, are some like a set of policies given by evolution, others are learned. That's one question. So, okay. Because they called me and I lost the flow of the idea.
Don't worry, Gary. I think we should pass to the next presenter.
Okay, so I will.
Great presentation, by the way.
Thanks a lot. Thanks for your feedback. So the last presentation is, I would like to present Consuelo Rojas. So she's a PhD candidate of the medical science program at the Universidad Católica. Her focus is on nanomedicine, nanotechnology, and biomedicine. Her main topics are nanosystems, oxygen, biomedical applications. And her poster is titled Novel Nanosystem Based on Perfluorocarbons for Biomedical Applications, Formulations, and Biological Evaluations.
Okay, thank you for your presentation. To start my presentation with introduction. The oxygen is a vital element and essential for cellular respiration. Without oxygen, the life of the cells are not possible, and the typical hypoxia situations are, for example, transplants, injury, transfusions, etc. The question now is, what can we do? We propose the use of oxygen carriers, for example, the nanosystems with perfluorocarbons. The methodology of my thesis project: first, I formulate different nanosystem formulations, and then we measure physicochemical characterization, encapsulation, and stability. Second, we measure dissolved oxygen levels in nanosystem formulations. And this formulation charged with oxygen previously. Third, we made a viability assays in 2 cell lines, HUG7 and HEG cells. Respect to my results obtained, the best results are obtained with negative surface nanocapsules. You can see the zeta potential negative and appropriate polydispersion index and good encapsulation efficiency. When conducting toxicity experiments, nanocapsules show low toxicity in both cell lines used. You can see different times and different concentrations of nanosystems, and you can see a good viability in both cell lines until 4 hours of the assays in 2 cases. By conducting oxygen transport experiments, we were able to determine that these nanocapsules can transport oxygen. You can see in this figure the perfluorocarbon in red and blank nanosystem formulation. And you can see the perfluorocarbon nanocapsules can transport more oxygen levels than blank nanocapsules without PVC. Finally, the conclusion of this project, we generate stable nanosystems with high PVC content and capable of efficiently transporting oxygen. We propose the use of these nanosystems in the biomedical area with special relevance, organ transplants, and blood transfusions. Respect to my future work, you can see I will make hypoxia assays in specifically immunofluorescence and Western blot of his factor. Finally, we will measure cell viability after hypoxia injury. Thank you for your attention.
Great, thanks, Consuelo. So now we start the questions and answers. Gonzalo, go on.
Thanks, Consuelo, for your presentation. This kind of nanotechnology and nanosystems are really interesting. I like it a lot. And so the transport of oxygen here is in the nanocapsule, right? So I understand the micella, like you make with the PFC, but what is inside that? What is inside the nanoparticle?
Inside nanoparticle, I use a perfluorocarbon, and then the surface is a negative polymer. This is answer? Or
okay, so the thing in the center is the perfluorocarbon.
Perfluorocarbon, yes.
And
yes, and this is a oxygen carrier because this compound this compound can capture the oxygen, and then you can see this graph, this figure, and you can see in this line red the PVC can transport oxygen more than the blanks without PVC.
So what means close and open? Close and open of what?
Repeat me, please.
In that plot that you showed before, no, the last one, I think. You have a line and you have a close and an open.
Okay, in the system,
Yeah.
you can see initial measure, and then you can see oxygen charge. You put into the formulation oximeter, a probe oximeter, and then you put oxygen in this formulation for 10 minutes, and then you close this system, and you can see the stabilization fast, and then you open this system, and you can see the dissociation fast, and the oxygen is free.
Okay, thanks, Consuelo.
Okay, so we have a question from Daniel.
Thanks. I have a question about the oxygen-loaded nanoparticle. What fraction of the weight of the actual complex is oxygen? Like hemoglobin's a big protein, but it carries, 4 O2 molecules. So is it like a big particle with a little tiny bit of oxygen, or does it actually lose a significant amount of its weight when it gets deoxygenated?
Okay. Okay. The cure of nanoparticle contained perfluorocarbon, and this compound can transport the oxygen, because the interactions of oxygen and perfluorocarbon is very stable in the time in this system. And the surface negative can confer a stability of system, because it's a negative, and the membrane cellular is a negative, and then it's very good for the cell, because these nanosystems can unit at the cell, but not into the cell, with a seropotential negative. The nanosystem interactive with membrane, but not into the cell. This.
Okay, and Consuelo, do you have a particular target or kind of cell?
No, the systems. My aim of my thesis is formulate nanosystems will be able to transport oxygen, but not the nanosystems can into the cell. This is the principal aim, and because my objective is a transplant, for example, perfusion of organs, or treatment of injuries in the skin, and this.
Mm-hmm. And if you compare the strength that have the red hematocrito, the red blood cell, yes, between the strength to the oxygen of this nanoparticle, you can do that comparison?
Yes.
Test the affinity. Mm-hmm.
This nanosystem is better than red blood cells, because it's more efficient than hemoglobin, because the interaction of my PVC with oxygen is more stable, and those depend of concentration of oxygen, but the hemoglobin depend of change conformational change for interaction with oxygen. But my PVC is a linear relationship.
And the last question, how it will deliver the oxygen? If it has a very high affinity, how will be attached the oxygen?
The liberation, dissociation. Okay, you can see if the association fast is very fast, and then the dissociation fast is more is less fast than in this fast. This association fast is more is faster than in this fast.
Okay, thanks. Thanks a lot, Consuelo. So if there is no more question.
Thank you.
Now it's time to have a little break. What about 5 minutes, and then go to the breakout rooms?
I wanted to give a final words on the presentations. I think it goes very well. Thank a lot to all the IBMers that participate in this networking to know each other work. As you will know, we are members. A lot of us are members of the Institute of Biological and Medical Engineering, and we aim for interdisciplinary work. In that objective, we are making this kind of networking to know each other researchers, because in the institute we're all grouped together, sitting next to the other, but we don't really talk to each other about our researches, or we don't have the visualization, the presentation, the proper tools to transfer our knowledge or to get known or research to others. So I'm glad that you participate and explain your research to your colleagues in science. So I don't know, I cheer up to everyone, and I hope see you in next events like this.
Thank you, Gonzalo.
Yeah, thanks a lot.
Thank you all for participating. So we should close, and then we meet in breakout rooms.
Yeah. So we'll see you in
We can make a break of 15 minutes if you want.
15 minutes?
Okay, see ya.
Okay, see ya.